Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Good morning. Good morning. I welcome you all to this first session of the third day of this conference, and this is the last day. I welcome our speaker, Professor Arup Kumar Das, and this session will be chaired by Professor Bonni Ray from IIT Delhi, and I just request Professor Bonni Ray just to start the session. Okay. What to Professor Bonni? Professor Bonni, you please speak.
Yeah, I am visible and I'm audible.
Okay. 1 minute. Please speak.
Hello? Yes, am I audible?
Yeah. Okay. Thank you, Professor Das.
Thank you, Dr.
Good morning. Good morning, Professor Dalal, Professor Ray. Good morning.
Yeah, so good morning. So today we are in the third day and this is the last day of the conference, and we again have interesting keynote lectures today. So it's my privilege to introduce to you Dr. Arup Kumar Das. So he is giving the first keynote lecture today, and his topic is on use of microfluidics for assessment of physical exhaustion level. So it will be an interesting talk. So let me introduce him. Dr. Arup Kumar Das is currently working as an associate professor in the Department of Mechanical and Industrial Engineering in IIT Roorkee. He has received his MS and PhD degree from IIT Kharagpur in the year 2006 and 2010 respectively. He is recipient of numerous awards, which include K.N. Sitaramu Award and Medal for Young Researcher by ISHMT in 2019, Young Scientist Award by INSA in 2015. His current research interests are focused mainly on two-phase flows, microfluidics, biofluidics, boiling heat transfer, and numerical methods. And he has authored more than 90 peer-reviewed journals and has 6 registered patents. And as I follow his work very much, so I see that he has done great work and his papers are highly cited and it has great impact factor. And most of the people who do multi-phase flow or work on microfluidics, they already know how Dr. Das works. Yeah, so thank you for the chance to introduce you. So the stage is yours. You can start.
Thank you, Professor Ray, for this nice introduction in the early morning. So I think Professor Dalal is also here. So thanks for giving me this opportunity to present over here in FMFP. So let me try sharing the slides first, and I'll be next.
Is the head of the department, and R.J. Reynolds, professor in mechanical engineering and mechanical aerospace engineering department at NC State University.
So, Professor Ray, is my screen visible? The slides are visible?
Yes, slides are visible. So, but there is some background noise. Can you just check? Somebody have to mute.
Space propulsion systems
Yeah.
Let me just check. Yeah.
Yeah, now it is fine.
Yes, yes.
The slides are visible, right? Yeah.
Yes, yes.
Okay, so once again, good morning to all of you. So as Professor Ray has already introduced me, so I'm working in Department of Mechanical Industrial Engineering, IIT Roorkee. And it's my privilege to speak to all of you on the occasion of this FMFP 2020, though it is not a physical meeting. And eventually I'm missing this last in the left-hand side corner 2 figures. These are IIT Guwahati figures. And I was fortunate to serve as faculty also in that institute. And in the left-hand side, you can see IIT Roorkee. Both are green and that eye-soothing campus, basically, I should say. Why I'm saying eye-soothing is because today in this hour, I'll be trying to talk with you about physical exhaustion. So, I do not know how to connect this topic with this framework of fluid mechanics and fluid power, but let me try. So we all know that physical exhaustion actually hampers our workability. Okay, so whenever we work for a prolonged hour, so we eventually find out that physical exhaustion is killing our efficiency. So to understand this physical exhaustion level, we don't have any assessment techniques so far. So what we do, we actually depend on some tests, etc. But that test is time taking. By that time, whenever you'll be getting the report, you will be actually finding out the hour of your exhaustion is over, and probably once again you are freshened enough or recharged enough to start your activity. So it is actually a need of in situ, or I can say instantaneous, measurement of the physical exhaustion level. So this work is targeted towards this. And microfluidics, how it is connected, I'll be trying to tell you very soon, but it is actually using some microfluidic panel to determine the exhaustion level. So that's why it is very much important in this conference maybe, that how one can use microfluidics for determination of the physical exhaustion level. Majority of the cases, microfluidics we use for some other purposes, like, biofluidics or the separation of molecules, etc., etc. But here we are trying to use this microfluidic channel for some other level, which is for the exhaustion level determination. So let me go to the next one. So all of us know, as I have told you, that strenuous activity. So if we do so for a prolonged period, so it will be causing you dehydration. And if there is dehydration, so you will be completely exhausted, right? So, and if you are exhausted, and then your exhaustion level will be actually giving you certain, detrimental issues to your health. It can also cause failure of vital organs, and to some extent, some extreme situations can cause you death also. Okay, so it is very difficult to find out the exhaustion level accurately. Okay, so and as I said, instantaneously. So we have to rely on majority of the cases our instinct. Okay, and it will be becoming very, very important whenever we are actually going for the important sectors like our soldiers, and to some extent whenever we are talking about athletes, so when they are competing in the national or international level, whether they are fully physically fit or not. This is very important for heavy vehicle drivers because they drive from one end of the country to the another end. Okay, so whether they are mentally or physically fit to drive the vehicle. So those are very important and pertinent question. Side by side firefighters and several other service sector where they are giving the prolonged service to us. So if you think about the person who is actually having 100% exhaustion level, so it will be actually causing some sort of poor physical and cognitive responses. Okay, so you'll be finding out that they'll be prone to make error, and due to that, there will be some sort of property loss, or in some cases, loss of lives also can happen. So with this small background that why it is needed for the society to understand that what is our exhaustion level. So let me take you to the next one, that this on-site determination and timely determination of exhaustion level is the need of hour. Okay, and if we can figure out a small kit which one can carry along with the person, so then it will be very useful. So from there only we try to understand that what are the methods to get the exhaustion level. So conventional approaches, whatever we are having, so that is actually measuring the exhaustion level in the lab. Okay, so you go to lab, they do some testing and then take some sample and finally give you the medical report. But this is actually what happens. This is expensive, obviously, and you have to find out a nearby medical facility first. Then you have to, spend some time over there because doctors will be examining you. They'll be taking the samples from your body. Different samples are being collected, and side by side, it requires some professional healthcare personnel. Okay, so that is also needed. So this is a conventional approach. What we are proposing actually some advanced point of care approach for measuring the exhaustion level. So what we have done over there, this is actually a lab-on-chip device. Okay, so everything is inside a small container. Basically, I'll be showing you the container. So this is actually inexpensive. Okay, and it is portable, first of all, and then side by side it will be very much interactive, accurate and fast. So quickly it will be giving you result. You need not to wait for somebody to analyze your sample in the lab and then find out that what is the exhaustion level. And no need of obviously the professional healthcare personnel. Okay, so that's why this is probably a good approach to determine the exhaustion level. So let me see that what are the different body fluids available which we can actually take for our development of this lab-on-chip device. First option we have is blood. We know that blood is the body fluid which in other lab tests also we prefer to take because this gives you the quick and fast result. Okay, but what happens, this is requiring some sort of proper sterilizing tools. Okay, and it requires trained professional also. And all of us know this is actually causing some distress to the person from whom we are taking blood. Like me, people are not liking to give the blood. Okay, and it is time consuming, obviously. So that's why we have not chosen blood to take in our microfluidic device. Another option is urine. Okay, so if you take urine, then also it can work. But what happens? This will be causing some sort of you will be requiring some sort of private place to collect the sample. Okay, and it is not always comfortable to deal with urine for a longer period, as because some smell will be also coming from urine. Okay, so that's why urine also we have discarded. And next option we had sweat. Okay, sometimes sweat also gives you the understanding that what is your exhaustion level. But what we found out is that sample of sweat collection is actually not uniform. Different person will be sweating differently, and there will be chances of contamination. Okay, and especially it will be failing whenever it is winter season, because winter season majority of us know that there will be no sweating. At that time it will be challenging to collect the sweat sample in the winter. So the device will be failing in the winter. So with this sweat also we have discarded. Then we have the last one, which is nothing but your saliva. So saliva-based diagnostics nowadays it is becoming very popular. Okay, and we see that it is actually non-invasive type, like where blood is actually invasive type, and it can be given at any place, any time. So you need some sort of private place, whereas sweat it is actually dependent on the time. In winter you cannot give, whereas saliva it can be given any place and any time. So that's why we have chosen saliva as our body fluid for this microfluidic kit. Okay. Next, if we have decided saliva to take, so then we try to see that what is the rheological behavior of saliva. So if we think about little bit biological details, that our central nervous system is actually having some parasympathetic nerves and sympathetic nerves. Okay, this figure actually tells you that in our nervous system which locations are actually connecting to the parasympathetic nerves and which are connecting to the sympathetic nerves. So now, but I will be trying to focus only in the saliva portion. So let us a little bit enlarge this portion. So you can see these parasympathetic nerves, which will be actually stimulating saliva. Okay, whereas the if you see the sympathetic nerve, so this will be actually inhibiting saliva. Okay, so due to this, what we'll be finding out? We'll be finding out that saliva composition and secretion due to sympathetic nerve, it will be creating a viscous saliva. Okay, whereas on the other hand, whenever we are having this parasympathetic nerve actually activated, at that time the saliva will be watery. Okay, more little bit lesser viscous. We try to attack over here, and what we have seen in literature also, people have actually given idea of this, that saliva can be used as body fluid for detection of the exhaustion, and they said that how the saliva, some biological content of saliva like cortisol, etc., that changes whenever you are having a prolonged work hour or extent of your exercise or running velocity, something like that. People have told already in literature. But all these exercise people have done in the lab scale. That means, you have to do some sort of biological treatment of your saliva sample, and then clinically they have to find out. So this was a hint to us. So from there, we tried to advance forward. And what we have done, we tried to figure out that what are the drawbacks of the existing techniques for this saliva-based exhaustion determination. So these earlier techniques, we have found out this is depending on mainly on biomarkers. So they are trying to see what is the presence of different biomarkers in the saliva, and from there only it has been determined, or it has been evolved. It requires definitely a costly setup where you will be analyzing, okay, and obviously trained professionals are required who will be analyzing and understanding the presence of biomarker. A normal person cannot do. Okay, it involves technicality, a layman cannot do. Okay, and this technique demands storage and transportation of saliva from wherever you are giving, from that place to the lab setup. Okay, and once again, after getting the report, to let the person know, you have to come to vice versa also. That means you have to do the transportation and storage. Okay. So this was the drawback of the existing methodologies. So based on this, what we have done, we have actually developed a kit, okay, which I'll be showing you in the next few minutes. So this technique is actually, once again, depending on saliva, and it is depending on the rheological property, as the last slide I have showed you, that it is changing the rheological property. It is non-invasive, as well as you need not to wait for your assessment for a longer period. Instantly, it will be giving you the results. Okay. Next, let me tell you that how we are actually fabricating our microchannel for this one. Then I'll be showing you that how this microchannel we have used. We have not followed the fabrication methodology, normal fabrication methodology for microchannel, whatever we are having in existing practice. What we have done here, we have used a mold and wear method. Okay, so this is the mold you can see, and we are having wear. Okay, so this is the mold and we are having wear. So in this mold and wear, what we have done, actually this mold is having a connection with two nut and bolts. Okay, so these nut and bolts are actually making the wear tightened enough in between the mold. And then whenever you actually pour the your PDMS substance for preparation of the microchannel, it actually creates one cavity inside the mold. And as a result, what you can find out is that this kind of methodology is exactly not requiring any clean room facility, and it is actually fabricating faster way the microchannels. And the major important thing is that we have seen when we have actually fabricated microchannel, whenever we connect the upper end and the lower end, there is chance of leakage. Okay, so this methodology will not be having any leakage. This is leakage free. And this is clean methodology, obviously, and so no dirty substance like you need not to age, you need not to do fuming. All these things are not necessary. So this methodology we have used as because we were requiring a very simple and straight microchannel in our device. Okay, and it has actually helped us also eliminating the costly equipment requirement for the fabrication of microchannel. So with this mold and wear methodology, we have progressed further. We have prepared microchannel, and I'll be showing you how the microchannel we are using in the kit. But before going to that, I'll be showing you the proof of concept, what we have established. So what we have done, we have actually taken our glycerin mixture, okay, so water and glycerin mixture to create different types of rheological behavior of the property. And we have seen that emptying of this water and glycerin mixture is actually dependent on the viscosity of the fluid. Okay, so what we try to do is that we try to find out for a particular amount of fluid what is the emptying rate for different viscosity. And we have found out that this kind of nature we have obtained while we have tested for a wide range of viscosity. And in this, we are actually looking for this viscosity range as because we found out whenever people do certain strenuous activity, the viscosity level of saliva varies in this range. Okay, so something in the range of, let's say, 7.5 millipascal second to highest it can be 30 millipascal second. Okay, so with this proof of concept that emptying of saliva we can use for determination of the saliva viscosity, and saliva viscosity is directly connected with the exhaustion level, we try to develop our kit. Now, in the right-hand side, I have shown you that small fluidic aperture for the kit, I should say. So here you can see this is the storage section of the kit. This is nothing but a conical funnel's upper portion. Okay, so here we actually store the saliva. Whenever somebody gives the saliva, we store it over here. And this is the approach section of the saliva so that smoothly it can enter in the microchannel. And basically, this is my microchannel. Okay, so we have taken fair amount of dimension over here, which is somewhere in the range of 500 micron only. Okay, not very small, smaller one. Okay, so smaller one we can do, but it will be actually increasing the time for the results to come. With this microfluidic platform, which is having a funnel kind of thing on top of a microchannel, we have used for emptying of the fluid, which is having different rheological properties. Okay, so and we have seen that emptying rate is varying. So with this proof of concept, we have advanced forward. Then we try to do different, calibration of this one. We try to do some strenuous activity like or running over treadmill or cycling for a prolonged period. And then we have done it for different temperatures. So today I'll be showing you temperature and humidity level of 25 degrees centigrade and 50% RH. And this we have done in a climate chamber at IIT Roorkee at different conditions from -20 to 50 degrees centigrade. We have achieved the results, and 20% relative humidity to in very humid condition also we have seen. And based on that, what we have done, we have actually tried to see that what is the emptying rate while we are having variable walking speed on the treadmill, as well as we have seen that how the emptying rate actually varies whenever you are doing a prolonged activity at a constant speed. Okay, so we tried to feed our data with this kind of exercise. So what is the key finding of this exercise? We found out that saliva emptying rate decreases with activity level. It actually rate decreases means viscosity increases. Okay, and it is following actually a polynomial trend. This is the major finding we have got from an enormous number of sample data. And then using this, what we try to do is that we try to see that what are the other parameters. Oh, by the way, before going to that, I'll tell you some sort of descriptive statistics of the human subjects we have used. So this is actually the human test subjects are having average age of 25 years. Their height is in the range of 173 centimeter and weight of around 75 kg. Okay, and with this, whenever we have done the exercise, so there are some exercise protocol here. I have mentioned exercise protocol over here also. You cannot take food or water before giving the saliva. So we have actually asked the samples, human subjects, to not take food or water before 120 minutes of the activity. And then, the climate chamber, you have to come and sit there for 30 minutes as a sedentary person, and then you have to give the saliva. So these are some exercise protocols we have mentioned, and we are measuring the pulse and the oxygen level of this one, SpO2, at different level of the exercise. Okay. And side by side, after doing the exercise, they are supposed to give the saliva sample. So there also, what we are having some sort of protocol. By the way, we give the saliva in a drooling method. It's not like, you have to cough or you have to spit. It is actually by a drooling method. So no breathing from mouth. Okay, so it will be breathing from your nose only, and we collect a very small amount, 0.2 ml of saliva. Okay, and it is actually then poured in the microchannel. So this is a representative figure. So quickly I'll be showing you that how we are doing. Then what we have found out, we actually found out that for different subjects, so these are different subjects, 1 to 7, I have shown here for 7 only. So different subjects at different walking speed whenever and different working time also whenever we have seen, we have found out the natures are different. So it is very much person specific that we have found out. To deal with that, the curve is polynomial, but where it is starting and what is the slope, what we have done to find that issue, what we have done, we have actually tried to find out that whether this kind of nature is actually validating the existing literature or not. So people have found out with heart rate. We have also tried to do so. And we have found out that heart rate based analysis is also matching with our polynomial analysis. Okay, for developing this kit. Also, we have tried to see from our different analysis scales, like we usually for exhaustion analysis we go for Borg scale or symptom scale. Okay, so these are questionnaire based scale basically for the human subjects. So there also we have found out that the perceived detection scale and whatever kit detection we are having, so that is actually matching with each other. Okay, so it is having a good match. So ultimately, we get the confirmation that probably this kind of tool may help in finding out the exhaustion level detection. But then our challenge was that it is very much becoming the human specific. So what we have done, we have actually programmed this device such a fashion that it will be taking the initial sample for the calibration of the device. So how we have done the calibration? So earlier I have shown you that the emptying rate was actually falling in a polynomial pattern. So we have fitted a polynomial. Here ER is emptying rate. Okay, so we have fitted in a polynomial pattern, and this polynomial constant we have listed down for different subjects. So this is the first subject. What is the polynomial coefficients? Okay, that we have listed down. And then what we have done, we have actually tried to see that these constants, how it is actually dependent on the emptying time and the initial level. Initial level means whenever they are not exhausted at all. That means whenever they are freshened up before going for the the activity. Okay, running on the treadmill or cycling or doing any other strenuous activity. Okay, so this if we find out, then we can actually get a unified relationship for all human beings. So that we have done, and ultimately you can find out this exhaustion level will be dependent on the initial time for emptying of the saliva, and at present whatever you are having the emptying time for the saliva. Comparing these two, we have actually evaluated what is your exhaustion level. Okay, so now let me quickly tell you that what we have done. First, you have to switch on the device. For the first time, device will be prompting you to give the saliva initial sample, and initial reading will be recorded, okay, in the non-volatile memory. Okay, so that will be first calibration, and then restart the device. The device is ready for your sample detection whenever you are taking the strenuous activity at that time. So this is a small look of the determination of the emptying level. We have used the this thermal conductivity based probe over here. Okay, so this probe is actually giving you when the saliva has started to empty and when the saliva has completed its this one draining, and then that we actually give to some electronic CPU, and then finally there is some sort of digital display. So with this, I'll be trying to show you what is the overall look of the kit. So this is the kit you can see in my left hand side, and you can see the dimension also. It is very handy to carry along with you. And this is the screen section view. What are the interior sections we are having? So this is the funnel at which one can give the saliva. Here it is the storage section. This is the approach, and then finally we are having the microfluidic channel over here, from where we actually allow the saliva to drain. And it is having some sort of the panel with which you can be interacting with the user. So it is quite interactive. It is lightweight, somewhere in the range of 130 gram. We have now devised. Okay, it is user friendly because it can be programmed and it will be giving you some message also. Okay, so with this, let me show you a small video for the demonstration. Let me see if I can run the video. Just give me a minute. Yeah. So you can see that it is actually giving you some amount of information over here. At the beginning, it is having low saliva, and then after giving the saliva, it will be with full saliva. Now saliva is emptying. And soon it will be telling you what is your exhaustion level. It has taken this much time to empty the saliva, nearly 41 seconds. This is the exercise protocol. You can see now he is giving the saliva by drooling method only. He is not spitting over there. And then it is reading, okay, the saliva sample. The saliva is full now. And then it is emptying. And then soon it will be telling you the level of your fatigue. So it will be telling you the fatigue. It is measuring the time for the that conductivity probe detection. And it is saying that what is the level of fatigue. It is having the medium fatigue. Okay. So with this, I want to stop over here. This is a small demonstration of our kit and the technical details. So this is a last message. What I wanted to give you is that physical exertion level is actually less discussed, but it is a critical parameter which can affect the the performance of the people handling critical jobs like soldiers, firefighters, etc. And finally, this one I would like to end my talk. Thank you. If I am having any question.
Yeah, thank you, Dr. Das. It was a really great talk, and the way, as you said, it was like some class we were attending. So from the beginning, different fluids, different techniques. It was really interesting. Yeah, so I will take some questions from the audience. So please raise your hand and you could ask your question. Now, any question from the audience? Yes, Dr. Sharma. Yes. Please unmute and yeah, you could ask.
Yeah. Thanks, Arup. It was a nice presentation. I perfectly agree with Bhani. My question is, I'm wondering, as far as the physical basis that you have used, how far it is established, because there is a scientific observation based on which your kit is based.
Yeah.
Good morning, everyone. I would like to welcome Professor Suman Ghosh from NIT Rourkela to chair the session. Sir, please.
Okay, thank you. Thank you very much. Good morning, everybody. Are you listening? My audio, my sound is audible? Are you
Yes,
listening?
sir.
Okay.
Yes, sir. Yes.
Okay. So first, I'm requesting Naman Agrawal, please present your paper with the paper ID 214. The title of the paper is Less Modeling of Volcanic Ash Particle Setting in Water Using the Adaptive Mesh Finite Element Method. Please start the video. Naman Agrawal is present here. Naman Agrawal present?
Good morning, sir. Yes, sir.
Okay, good morning. Good morning. Okay, start the video.
Hello, everyone. I'm here to present my work on LES modeling of volcanic ash particles settling in water flows using an adaptive mesh finite element method. This is the brief outline of my presentation, and let's start with the motivation behind this work. Now, turbulence has been encountered in nature. Volcanic eruptions are one such phenomenon in which the ash particles travel to a large distance and finally settles in the seabed. Now, during the course of action, the flow gets turbulent, which causes variation in the rate of ash depositions. These depositions are of great geological significance as a vast information of volcanism is contained in these. Hence, understanding of these flows is extremely critical. Now, turbulence is basically defined as a high Reynolds number flows which causes diffusion of mass, momentum, and energy. They are characterized by eddies of various length scales, the smallest being the Kolmogorov length scale, which is universal in nature, whereas the highest one is the integral length scale, which is anisotropic. As the variation of length scales are high, the experimentation is critical and does not provide a complete information of the flows. Hence, numerical approach is being taken in the current work to get a bigger picture of the dynamics of these flows. In the past, the turbulence has been modeled using three different approaches. The first is the direct numerical simulation, or DNS, which actually resolves the each and every scale of turbulence. During this, the accuracy of the solution is highest, but at the same time, the computational cost increases significantly. On the other hand, Reynolds average Navier-Stokes equation, or RANS model, is economical and used industrially, but they lack accuracy due to its simplifying assumptions of modeling each and every scale. Hence, LES is used as a bridge between these two models, as it resolves the large scales of motion and models the small universal scales. These are the basic governing equations pertaining to multi-phase flows in Olenian approach. Alpha represents the phase volume fractions, U is the velocity, the gravitational force is taken into consideration, and Fi represents the interface interaction term, which is drag to be prominent in the present scenario. Now, the LES works on the filtered decomposition, in which the velocity is being decomposed into a filtered part and filtered part using a convolution filter. Hence, the equation is solved for the filtered velocity. The unfiltered velocity is taken into account by a stress term, which is tau T as SFS stress, and is modeled uses Bosnick's viscosity hypothesis, which states that there is a linear stress-strain relationship between the filtered rate of strain and SFS stress. Here, mu t represents the flow property and is anisotropic in nature. The final momentum equation, that model equation, is solved in finite element approach is this. Now the finite element framework is being used here because of the ease of using unstructured mesh and getting the higher order accurate solutions, which is difficult to approach in finite volume method. Now for simplicity, a single phase modeling is used for illustration. In continuous Galerkin approach, the whole equation is multiplied by a weighted function and integrated over the domain to get the weak form of the solution. Then the variables are approximated at the nodes where xi j and phi xi I represents the trial functions of the solutions, and these are put back into the weak form to get the final discretized form. Now the discontinuous Galerkin approach is similar to the continuous Galerkin approach, but the only difference is instead of integrating it over the domain, it is integrated element wise and the elements interact among themselves through flux terms. Now the SFS stress with the mu t is modeled using LES models, the first being the second order Smagorinsky model, where CS represents the second order Smagorinsky coefficient and delta bar is the width, which is a multiple of the mesh size. Mod S represents the strain rate modulus, and this model is economical in nature, but it has certain limitations. Later, the dynamic tensorial model was developed to account for anisotropy of the mesh, and the CS values changes dynamically with time. Now the mesh particle settling operations is being performed, which is a multi-phase flows, and hence mesh adaptivity is taken into account, which actually optimizes the mesh dynamically, hence reduces the computational cost. It is divided into basically three different steps. The first is the metric estimation, which calculates the error matrix. The second is whether the error is within the permissible range, and if not, the mesh is modified by either adding the nodes or removing the nodes. And the final step is the field interpolation, where the field variables are being transferred from the older mesh to a new mesh. Now the ash settling in a water tank is being performed numerically with the geometry with length equal to 0.3 meters and height as 0.7 meters. And water is considered as a continuous medium, and ash particles are treated as discontinuous terms. The first work that is done is the grid sensitive test. For that, 3 different meshes were used with 15,000, 45,000 and 1,35,000 nodes. As you can see in the graph, the particle settling will time, and as you can see, the red one, which is FM1 mesh, the behavior changes significantly, whereas the FM2 and FM3 shows a similar behavior. The FM2 mesh is economical in nature as it is 600% times much smaller or economical as compared to FM3 mesh, and hence it is being used in the subsequent studies for comparison with adaptive meshes. For the effect of adaptive mesh adaptivity, FM2 mesh was taken into consideration, and 2 different adaptive mesh were taken with maximum minimum size are being taken as defined in the table. As you can see in the graph, there is no clear behavior of the tephra velocity which takes into account during the course of simulation for 240 seconds, and this is because the mesh is adapted with time and hence eddy viscosity changes. This is more prominent when you see at t equal to 80 seconds, the mesh at the inlet is being refined and hence eddy viscosity is reduced, leading to a variation in the dynamics of the flow. Hence, mesh adaptivity should be used with LES with proper consideration of mesh sizes. Further, LES turbulence model was tested whether it has an effect on the flow dynamics or not. For that, 4 different cases were taken where no LES represent, there is no turbulence model that has been included, and LES means when the second order Smagorinsky model is being taken into account. As you can see, at t equal to 140 seconds, the flow dynamics changes significantly and the tephra velocity increases, leading to a eddy formation at t equal to 200 seconds. This is clear when you see the graphs at the laminar zone, where the DG LES and no LES velocities matches well with the Stokesian formulation. However, the CG formulations do not show a clear match with the theoretical formulation. This is because of the strongly imposed boundary condition. And on the other hand, when you go to the turbulent zone at t equal to 120 to 180 seconds, the CG results shows a 10 times increase in the maximum tephra velocity, which is similar to the results obtained by Carey in his experiments. Hence, CG LES model was used further to test the effect of different LES turbulence models. For LES turbulence models, the second order Smagorinsky model was compared with dynamic tensorial model, which uses 2 filter widths, alpha and beta. Alpha represents the first filter width ratio, which is the ratio of first filter width to the mesh size, where beta represents the ratio of second filter width to the first filter width. As you can see in the graph, the 4 different combinations were taken, and with alpha equal to 2, the results match well with the second order Smagorinsky results in the turbulent zone. However, the dynamic tensorial model was computationally expensive as compared to second order Smagorinsky model, and hence a clear judicious choice should be made in dynamic tensorial model considering the computational cost of the simulations. For the effect of different tephra particles diameters were considered. For that, 4 different tephra particle diameters were considered, and as you can see in the laminar zone, the smallest particle diameter has the lowest velocity, which in turn in the turbulent zone reaches the maximum velocity in the at 140 seconds to 180 seconds. Hence, there is a clear variation or flip of the behavior from laminar zone to the turbulent zone. Hence, it can be concluded that the maximum tephra velocity matched well with the Stokes formulation in the laminar zone, and LES clearly demonstrates the importance of turbulence modeling in edge settling simulations with an understanding of the different models. I'd like to thank the HPC facility of IIT Mandi for helping me in my work in computing the numerical experiments for the present work. Thank you.
Thank you, Naman, for your nice presentation. Any question from the audience? Any question from the audience? Hello. Okay, Naman, I have a simple small question.
Yes.
Have you validated the results with any experimental work or some numerical work?
Sir, for the current problem, the only validation was till the laminar zone strokes, and nobody has modeled as settling case for the turbulent zone.
Okay.
So this is the novelty of the work, along with mesh adaptivity.
Thank you very much. Next, I'm requesting this Nilojendu Banerjee. Are you present here?
Yes, sir.
Okay, please present or start the video. I'm requesting the volunteer to start the video of the paper with ID 225. That is the dynamics of thin film over flat rough surface moving with a specified velocity.
Good morning, everyone. My name is Nilojendu Banerjee. I am pursuing my PhD from Applied Mechanics Department IIT Madras under the guidance of Professor Satya Narayanan Seshadri. Today my topic of discussion is thin liquid film dynamics over flat rough surface moving with a specified surface velocity. Now this is the outline of the presentation: introduction, approach, mathematical modeling, result and discussions. Now we all know post-collision of liquid droplet in the form of thin liquid film on various surfaces has enormous application in various engineering fields such as liquid jet printing, turbine blade cooling, spray coating, etc. Now in many practical applications, it is observed that surface always exhibits some amount of surface roughness and moves with a specified velocity. Lot of researches have been done to understand the actual physics behind this phenomena. Still, lot of insights are needed to understand the actual physics which govern this mechanism. Now, governing equation of liquid lead is used with appropriate boundary and interfacial conditions. Here we assume the lubrication approximation to analyze the governing equations. This is important because here we assume the initial liquid film thickness is very, very small compared to the horizontal length of the plate. Interfacial behavior is captured in the form of transient film equation. This equation is discretized using finite difference scheme and solved with the help of MATLAB. Now, this is the mathematical modeling of our present work. Here we can see that the surface is maintained at a constant temperature Tw and moves with a specified surface velocity Uw in the right direction. The d or the small d is here the initial film thickness, Ti is interface temperature and T0 is surroundings temperature. And the portion enclosed within the circle is considered as the surface roughness, C bar, which is defined as the roughness per unit length of the plate. These are the non-dimensional governing equations of liquid layer. These are the boundary conditions at y equal to 0 and y equal to delta. Now this is the non-dimensional film thickness equation, and from this equation we can find delta bar, and with the help of this delta bar we can also find average and local Nusselt number. Now this is the validation of our work. We compared our result with the numerical study of Ajay et al. The validation could have been much better at the initial length of the plate, but for the larger distance of the plate, the accuracy is very good. In the results and discussion portion, the variation of surface velocity and surface roughness is observed on dynamics of film. Results consist of effect of surface to surrounding fluid temperature difference in terms of non-dimensional Marangoni number capital M, effect of different surface velocities on film thickness, effect of different surface roughness on film thickness. And for each case, we also analyze the heat transfer in form of non-dimensional Nusselt number. Now, if we increase wall to surrounding fluid temperature difference, heat transfer from plate to interface also increases. And due to this, the temperature difference between interface and the surroundings is increased, and due to this, undulation is pronounced on the interface of the film. Now, figure 3 shows the variation of film thickness with respect to x bar for various Marconi numbers. And figure 4 represents the Nusselt number variation with respect to X bar for various Marconi number. For high Marconi numbers such as m equal to 16, a small instability is observed very near to the plate, which induced a fluctuation of Nusselt number at the initial length of the plate. Now, if we increase the surface velocity for a smooth surface, the maximum height of the film peak is shifted continuously towards the plate motion. And this is because of the inertia effect that is induced by the moving plate into the film, which increases the heat transfer. Figure 5 represents the variation of delta bar with respect to X bar for various U bar. And figure 6 represents the variation of Nusselt number with respect to X bar for various U bar. Now, if we consider a smooth surface and if we increase surface roughness value, then we can see the peak of the film thickness does not shift because of static nature of the plate, but the thickness of the film decreases. And as surface roughness increases, there is less contact between solid and liquid, and due to this, heat transfer rate decreases. Figure 7 represents the variation of delta bar with respect to X bar for various C bar. And figure 8 represents the variation of Nusselt number with respect to X bar for various C bar. Now, we also analyzed the effects of both surface velocity and surface roughness on average Nusselt number. Now, figure 9 represents the variation of average Nusselt number with respect to the non-dimensional plate velocity for different C bar. Now, from the figure it is observed that for a particular value of C bar, if we increase the value of UW bar, the average Nusselt number increases. And this increment is sharp for smooth surface. But as we increase the value of C bar, then this increment slows down. This is basically because of counteracting nature of surface velocities and surface roughness. Now, in the conclusion portion, we conclude that for smooth surface, which is static in nature, if we increase wall to surrounding fluid temperature difference, heat transfer increases, and due to this, undulation of the film increases. For smooth surface, if we increase the surface velocities, maximum height of the liquid film is continuously shifted in the direction of the plate motion due to the inertia effect, and due to this, heat transfer increases. Surface with zero velocities, if we increase roughness, the peak height of the liquid film is continuously decreasing because surface roughness creates a damping effect on the film. Also, there is a less contact between the projected area of the surface and the fluid. As a result, heat transfer also decreases. These are the references.
Thank you, Nilajendu, for such a nice presentation. Audience, if you want to ask any question, you can ask. Any question from the audience? Okay. Nilajendu, have you compared the results with some experimental results or in the validation or some numerical results?
Sir, actually, the validation, that is the Ajay et al. Is basically a numerical simulations.
Okay.
But we cannot actually compare this with till now with experimental results.
Okay. Okay. And another thing that you have mentioned in the paper that the maximum error from the results with which you have compared, that is Ajay et al. Results, you have got 11%. That means the longitudinal error means the thickness error.
Yes, sir.
maximum thickness error. It is not the average error, na? Or
No,
it
no,
is
this is the maximum thickness error.
okay, thank you. Thank you very much.
Thank you, sir.
Now, I want to request Sachin Tom. Are you present here, Sachin?
Yes, sir. I'm present.
Okay. So I'm requesting volunteer, please start the video of the paper with ID 229, the numerical simulation of flow boiling in a vertical annulus channel under near atmospheric pressure condition.
Myself, Sachin Tom. So I'm presenting my work on numerical simulation of flow boiling in a vertical annulus channel under near atmospheric pressure conditions. So introduction. The two-phase flow with phase change involving gases and liquids is a complex phenomenon with wide range of flow structures such as dispersed flow, separated flow, depending on the liquid and gas fraction distribution. It plays an important role in several practical applications, including
Hello.
Yes, sir.
Is there any problem you are facing?
No, sir. I muted Nilojendo. He was actually he unmuted himself and then he started
Okay.
speaking.
Okay.
density is 2 orders of magnitude higher compared to the high pressure cases. The possible flow regimes under low pressure flow boiling conditions are the bubbly flow regime, slug regime, churn turbulent annular mist flow regime, and the fully vapor regime. So development of a CFD based model to capture the low void fraction regime, that is the bubbly flow regime, and the high void fraction regime, that is the slug or churn turbulent regime, at near atmospheric pressure conditions within the subcooled flow boiling is the scope of current study. Methodology: the heat transfer and fluid flow analysis of water in an annulus of hydraulic diameter 18.5 mm and 1670 mm heated length is considered here. So the domain considered is shown here. So it is a typical near atmospheric pressure water flow boiling conditions by Lee et al. So that case is simulated here. So a 2D axisymmetric model is developed for the flow boiling simulation of water at near atmospheric pressure conditions in the annulus channel. Initial and boundary conditions. Water flow boiling simulations for the chosen annulus is carried out with different mass flux and corresponding heat flux and inlet subcool. The boundary conditions considered here are typical experimental cases of Lee et al. And is shown in the table here. So near atmospheric pressure conditions is taken here and 3 set of mass fluxes from 474 kilogram per meter square second and 714 and 1015 and corresponding heat flux values is considered. So no slip boundary condition is used for the wall liquid surface and specified shear conditions for the wall vapor surface. Numerical procedure. So the two-phase flow and heat transfer case is solved using the Eulerian multi-phase flow model, that is the two-fluid model, and with RPI wall boiling model for wall heat flux partitioning. the realizable K-epsilon model with standard wall friction mixture-based two-phase turbulence treatment is applied for the simulation of turbulence. For the special discretization, first order upwind scheme is used and time derivative time using the first order implicit scheme. The phase coupled symbol algorithm is used to couple pressure field and the velocity field. The solution was considered converged when the equation residuals dropped below 10 raised to minus 4. Grid independency study. So 3 grid patterns of 2250, 4000 and 6250 cells have been considered for the study. So the vapor fraction variation along the radial direction for mass flux 474 and wall heat flux of 152.3 for 3 set of grid is being shown here. So it can be seen that 4000 cells is fine enough to model the heat transfer and fluid flow in the annulus. So a grid of 20 cells in the radial direction and 200 cells in the axial direction have been used for all subsequent simulations. So the results and discussions. The results shown here are for a mass flux of 474 and wall heat flux of 152.3. So the radial vapor fraction distribution is shown. So it can be seen that maximum occurs near the heated wall, inner heated wall, and it reduces to 0 towards the outer wall of the annulus as observed in the experiment. So the wall peaking behavior is being properly predicted, which is characteristics of the bubbly flow regime. So the maximum deviation in vapor fraction between numerical and experimental is around 12%. And the axial area weighted average at each section vapor fraction variation along the axial direction is shown. So word fraction versus thermodynamic quality is shown. So it can be seen that maximum area average fraction observed is towards the outlet of the heated section and is around 7%. So the radial vapor fraction variation for mass flux of 714 and 1059 kilogram per meter square second are shown here. So it can be seen that when mass flux is increased from the earlier case of 474 kilogram per meter square second to 714.4, the peak void fraction near the heated surface got increased. And in case of 1059 kilogram per meter square second, so here the mass flux is high and the subcooling also higher compared to 714. So here subcooling is almost 18 degrees, whereas earlier it is 14 degrees. So because of that, the peak has got reduced as well as the bubble boundary layer thickness also got decreased in the radial direction. So the extension of the vapor fraction distribution in case of 1059 is almost up to till 0.5, whereas it is extended till 0.7 in case of 714.4 cases. And the deviation with respect to experimental results for 714.4 mass flux case is 16% and for 1059 is around 17%. So the vapor velocity predictions is also shown. This and compared with the experimental, so it is higher near to the heated boundary. So the results shown are for mass flux of 474 kilogram per meter square second and 152.3 kilowatt per meter square wall heat flux. So the liquid velocity variation also shown here, and it deviates from the single phase flow due to non-uniform void fraction and vapor velocity distributions. As expected, higher velocity are obtained near the heated wall, which reduces towards the outer adiabatic wall. To capture the high void fraction regime, that's a transitional regime, the wall heat flux is further increased from 152.3 kilowatt per meter square to 250 kilowatt per meter square in steps, keeping the inlet flow rate case of 474 kilogram per meter square second. It is observed that void fraction moves on to the core region, showing core peaking behavior with highly oscillatory nature, which is resemblance of slug or churn turbulent regime. So the radial vapor fraction variation is shown here. So it can be seen that near heated wall minimum is observed with the maximum reaching towards the core region. Also the axial area weighted average vapor fraction with thermodynamic quality is shown here. It can be seen that maximum vapor fraction occurs towards the outlet of the heated section and is almost 60%. And this also confirms the existence of transitional flow regime in the flow channel considered. The vapor velocity variation is shown here for same mass flux case and wall heat flux of 250 kW per meter square. So it can be seen that maximum vapor velocity occurs at the core region because of lateral migration of bigger size vapor bubbles due to buoyancy. The wall temperature variation as well as the bulk fluid temperature variation also shown. So the wall temperature varies from 388 to till 391 Kelvin along the axial direction, and the bulk fluid temperature varies from 370 to almost 382 Kelvin. So the bulk fluid temperature maximum is observed at the outlet, that is around 382.59 Kelvin, which is less than the saturation temperature for the considered case. So subcooled conditions prevails at the outlet for the wall heat flux values considered. So this is the vapor fraction distribution. So the shown towards the end of the heated region it is shown. So it can be seen that when wall heat flux of 152.3, so the wall peaking behavior is seen with maximum void fraction reaching almost local void fraction reaching almost 0.224. With increasing heat flux to 200, the vapor having tendency to move towards the core region, and maximum local fraction reaches almost 0.7. And when it increases to 250, maximum fraction has been reached towards the core region in the end of the heated region. So this is vapor fraction contour distribution for mass flux of 474 with increasing the heat flux. The wall flux partitioning component variation along the axial direction is shown here. So the evaporation, quenching and the single phase convection part variations. So it can be seen that due to presence of smaller bubbles, the quenching part becomes more significant throughout the heated wall. And the evaporative part continuously increases from inlet to outlet, whereas the single phase convection continuously decreases, which reaches almost zero towards the outlet of the heated section. So also the evaporative part becomes significant with rise in heat flux from 152.3 to 250. In 150.3, evaporative part is only 20% of the total heat flux, whereas it becomes almost 47% with rise in wall heat flux to 250 kilowatt per meter square. So the conclusions. CFD simulations for subcooled flow boiling at low pressures in an analyst channel have been carried out by developing oil layer based flow fluid model. So the radial characteristics of local void fraction, vapor velocity and liquid velocity have been obtained and compared with the experimental results. The transitional regime characteristics are captured for mass flux case of 474 kg per meter square second by increasing wall heat flux from 152.3 till 250 kilowatt per meter square in steps. The maximum area average fraction observed at the outlet was almost 60%, which confirms the transitional flow regime prediction capability of the model with the incorporated interfacial constitutive relations. And further, the model has to be extended to simulate the saturation flow boiling conditions, which will be observed under high heat flux conditions. Thank you.
Thank you, Sachin, for your nice presentation. Then I want to request the audience, if you have any question, you may ask now. Audience, please, if you have any question, please ask. Okay, no question. Okay, Sachin, I think you have used any commercial software or you have coded it yourself?
So commercial software only, ANSYS Fluent I have used.
Okay, you have used ANSYS Fluent. Yes. And you have used Eulerian model. Achha, how many momentum equation you have used?
So momentum equation for each phase, for liquid and vapor phase.
That means you have used 2 momentum equation and 2 continuity equation.
Yes. Yes.
Okay. Okay, the interpenetrating was allowed or not in between the phase?
What's
interpenetration.
Interpenetration is that is not allowed.
I think in this Eulerian 2 fluid model, as you are using 2 momentum equation, I think interpenetration is allowed. Means
yes, through constitutive relations we will give the interacting effects. Some constitutive correlations are there.
My question is simple. In each cell, you have the computational cells. Now, in any cell, have you allowed both the phases or any single phase?
Both phases are there in any cell.
Good. Thank you.
Yes.
So now I want to request Aritra Mukherjee to present your paper, and I'm requesting Aritra, are you present here?
Yes, sir.
Okay. So I'm requesting volunteer, please start the video of the paper with paper ID 244, the numerical investigation of the effect of surface technology on droplet condensation following lattice Boltzmann method.
Hello everybody. Today I am presenting our paper on the topic numerical investigation of the effect of surface topology on droplet condensation following lattice Boltzmann. First I will introduce about the condensation of rough surface. Then I will tell about the formulation as we are numerically simulating the problem. There is a short formulation. This formulation will be presented. The results obtained in the conclusion process. Now, if we have to tell about the condensation process, we can see that condensation can happen in two ways, film and drop. It's very basic procedure. That when vapor comes to the contact with cold wall, it is hydrophysical liquid form. It is a vertical wall and the liquid is going downward. So this kind of shape. But for a hydrophobic surface, vapor condensation drops. And if the external force is applied properly, the movement drops. So that is drop-wise form. The problem with liquid film condensation is film completely covers the cold surface, which decreases the water heat transfer. But in dropwise condensation, we can clearly see that there are spaces where vapor can come into contact with the cold wall. So the heat transfer rate is actually high. Research shows that heat transfer rate in dropwise condensation can be 10 times higher in comparison to film-wise. Hydrophobicity of a surface promotes dropwise condensation, but practically achieving DWC on a cold surface is very difficult. So our basic target always is to achieve DWC, linear heat transfer. Here comes the importance of rough surface. Rough surfaces increase hydrophobicity, which in turn helps condensation of liquid as drops. That for smooth engineered particles, the conductivity may be as high as 180, but we cannot go beyond. But with using proper structures, like lotus speed structure, for example, we can say about lotus speed structure, the wettability of a surface is changed. Depending on the roughness topology and wettability, liquid can form Cassian Wenzel. Now, what is Cassian Wenzel drops and what are their importance? Wenzel drops are very common. Most of the cases, Wenzel drops are formed. If the liquid propagates inside the roughness group, so this picture when the liquid condensed and propagated inside the roughness groups, Wenzel drops form. Formation of Wenzel drops lead to film-wise condensation as the drops come from the surface and drops large, the movers fill. But in case of aegis, basically due to the structure, roughness structure, the liquid cannot propagate inside the structures. The contact angle is increased to 30-40 degrees. The liquid droplet sits on the ridges, and with proper external force and droplet removal mechanism, we can achieve dropwise condensation. So proper designing of surface structure can be dropwise condensation. And here comes the objective of our work, where we have taken two different surfaces, usually one single surface with two different roughness topologies, and we check that with which kind of roughness topology we can achieve Cassian state, which will lead to dropwise condensation, which ultimately increases the transfer. Now, research and condensation process may be divided in two steps. Experiments are going on. We are not telling about the experiments. They are very difficult to do. In numerical simulations, conventional approaches are there. But the problems with the conventional approaches are they are very time consuming and they need an assumption of initial interface. Like initial phase of the process cannot be simulated. Like when a droplet nucleates on the rough surface, it can droplet on the top of the exposed side or on the bottom. But we cannot simulate that. We always have to trace a basic droplet, nucleated droplet, and we can study the growth and movement of the. This is the advantage of the lattice-Boltzmann method. This is where lattice-Boltzmann method actually comes. We can achieve automatic phase separation. There are no assumption of initial interface. We can separate the different growth, and the method is also very fast. Our simulation takes only 30 minutes to do the whole simulation. But the problem is it does not work for very high density ratio. So for high density ratio problems, exact validation we have to go back to convention. Then there is what is the importance of lattice Boltzmann. Qualitatively, we can predict the nature of roughness topology, the nature of the roughness, the nature of the problem, with what kind of roughness qualitatively we can achieve dropwise and fieldwise, and where the nucleation begins, which we cannot predict the problem. So, consider the behavior of correction of particles. That microscopic factor is divided into volumes. The microscopic approach is study the individual particles. This is our lattice Boltzmann formula I am showing in short. I am not going to detail. We are using Shantin-Chiobuck model. Basically, there are 4 models, but for common multi-phase simulation, boiling and conventional problem, modified Shantin model is the most popular. It is used for the last 5-6 years for simulating boiling and conventional problems. In these problems, inside the basic LV with an added force term, we incorporate interparticle interaction force, which help us simulating the multi-phase problem. I will show it in the next slides. Now, this is the external force term simulation. Exact difference. But this is the equilibrium particle distribution function, density, velocity, and frequency of the fluid. We are using determinant lattice here. The weight factors and velocity factors are given. External force. External force consists of 2 kinds of forces. One is velocity force, which is very common. Another 2 forces are interparticle interaction force and surface velocity, which comes from the Shantin. In Shantin model, basically the Shantin force depends on the information about specific dependency of the force and the local density value. Here we can see that 2 fluids are there. For one particle, they are around that 9 particles are there from 2 fluids along inter. So their local density values helps in forming the function. But instead of using density function directly, we use potential function to use the differential solution. Instead of using the density function, we use the concept of which is realistic inside the body. We are using determinant here, this is the temperature and summary decrease. Now we are going to the results. At first, we have to validate our model in our score. So this is that we are depending on Laplace test and Maxwell area construction. Laplace test is very simple. Laplace test is fixed for a liquid drop or a beta. The difference between inside and outside pressure must be proportional to the inverse of it. So here the periodic domain will initiate the liquid droplet for different surfaces and check the pressure difference, plotted the pressure difference and the inverse areas. We expected a straight line and the straight line is obtained. So we state that our model can set the interface correctly. We are coming to the Maxwell area construction curve validation. In this case, we plotted the reduced temperature against the reduced density. Basically, Maxwell area construction curve tells us, it gives us specific density values for specific reduced temperatures. So those values obtained from our LBM code should match with the analytical values. Here we can see the match clear. We are doing the simulation induced temperature 0.9. So we match up to this point. Here is sufficient. This is the validation for our condensation model. The Nastran's polymetric problem is very common. The vertical wall is taken, the vapor domain. Now vapor condenses on the wall and flows downward. So to simulate that, we have created a domain where a mostly cold wall constant temperature is taken on the left side. Top and right surface are taken as constant temperature drop. Very gravitational force downward out to wall. According to Nastran, this is the condensate film thickness, this is the heat transfer coefficient. So we can see that our values obtained from our in-house code matches with the analytical values well. Now, after validating our model, we are studying The condensation of the paper aegis. So we have taken a 240 plus 240 domain. A cold spot is taken with 40 lattices. So gravity is basically there. So we are just studying what kind of droplet is forming. The initial temperature of the domain we kept as 0.9 of critical temperature and cold spot is 0.8 of critical temperature. Now two types of surface we have considered. This is the width of the fridge, the distance between two ridges, this is the height. So WS is equal to 4 lattices, GS 7 lattices, and HS 20 lattices, GS 1, and GS 2 means width 4 lattices, distance 8 lattices, and height 8 lattices. Now we can see the cases of formation. And first, we have the cases of formation, where you can see droplet drop actually condensing on the top and side of the ridges. And finally, it moves upwards due to surface tension force. It from the ridges. So this is the cases droplet formation. So when we apply any external force like gravity force in this direction, basically this is the vertical wall, gravity force will act in this direction. So it will form a zero. This is the match with another paper, wherein qualitatively matched with the length. With the length. Here we have started the one drop formation. The compound surface one drop is here. If there are several cold spots, we will go to film-wise condition. We have compared the liquid condensate accumulation rate for surfaces with different roughness parameters. You can see that for Wenzel state, droplets condensation start early as the surface goes to more hydrophobic. And for more hydrophobic surface, there, droplets start later. But eventually, they meet at a point. And with external force, the heat transfer will be higher for clockwise. If the roughness pillars with a larger height and shorter spacing, then formation of cathode droplet. Shorter pillars with wider spacing between them, so much Wenzel depth. These are the main conclusions.
Okay, thank you, Aritra, for your nice presentation. Audience, if you have any question, you may ask, please. Okay, Aritra.
Yes, sir.
Acha, when you are during competition, how much means what was the ratio between the time, the real CPU time and the real simulation time, means real time?
Yes, sir. CPU time is very low actually. No, I haven't checked real time versus
compared
CPU
to
time.
compared to the other
compared to other methods.
Yes. Achha, is it the reason that only due to that you have adopted this lattice boundary method, or to capture the interface also you have some more advantage, or it can capture the interface more prominently?
No, sir. Actually, there are two advantages. One is definitely real time. Okay.
One you are mentioning time, and one you have mentioned that regarding the initial assumption.
That is another
No,
reason.
I'm not talking about that. I'm talking about the fact that when you are capturing a complex interface, in that case, how can you compare this lattice Boltzmann method and this existing viewer method or other method?
Actually, sir, lattice Boltzmann method doesn't capture interface. Okay, it produces density values, and
I want to say that the shape of this drop for this condensation model with time, how the shape is changing, this phenomena. So
actually, all other methods tracks interface. Okay, all other methods track interface. That is Boltzmann method does not track interface. Okay, it just provides the density values. We take the average density values. Below that there is liquid, and above that there is vapor. Below that there is liquid. Okay.
Yes.
So that is the main fundamental.
So means have you simulated this work with using some other method?
No, sir. No, sir.
Okay. Thank you very much, Aritra.
Yes, sir.
For your nice presentation again. And audience is not asking any questions. So now I am requesting Mohd Khasan to represent your paper, or at the same time I'm requesting, actually he's not depending, actually volunteer will start the video. So I'm requesting volunteer, please start the video with the paper with paper ID 250. I think it is the last paper.
Greetings to everyone. My name is Mohammad Kashan and I am from IIT Guwahati, and now I am going to present on the topic a comparative study of space currents for cubic equation of state for E4, E6 and E8 order of isotropy and contact angle measurement using pseudopotential lattice-Boltzmann method. So what are spurious currents? Spurious currents are nothing but undesirable velocities present in the fluid flow simulation, especially in the interface region between different fluid phases. So as we can see in figure 1.1 on the right side of the slide, it shows the simulation of static droplet. So figure 1.1a represents the density distribution in a 2D domain with liquid droplet defined at the center in red color, that is higher density region, and surrounded by vapor density represented by blue color region. Here black dots show the nodes or lattice sites where maximum magnitude of spurious currents are present, and these large magnitude of spurious currents causes the numerical instability of fluid flow simulation. In figure 1.1b, we have the spurious currents magnitude variation in the whole domain, and again in the liquid vapor interface region, we can see large magnitudes of spurious currents as shown in red color black dots, while blue region represents small magnitudes of spurious currents. So these spurious currents are dominant in the interface region. This is the preview of the entire work. So using modified pseudopotential lattice-Boltzmann method, the comparative study of spurious currents magnitude are carried out. This methodology is validated for Young-Laplace law, as well as contact angle measurement is performed, and comparison of spurious currents are done for 3 cubic equation of state using 4th, 6th and 8th order of isotropy tensors. Lastly, multi-component multiphase LB simulation is carried out. So in figure 4.1 shows the neighboring particles that are considered in 4th, 6th and 8th order of isotropy in calculating the particle interaction forces, and weights associated with these neighboring fluid particles are mentioned in table 4.1. This is the methodology. Lattice-Boltzmann method is one of the popular and newly developed mesoscopic approach for fluid flow simulation. There are some of the advantages of LBM, such as ease of dealing with complex boundaries and ability to capture multi-fluid physics, etc. So in our study, we have used pseudopotential lattice-Boltzmann method, which was introduced by Shannon Chen in 1993. It provides simple expression that relates the interaction forces between discrete fluid phases and each fluid's equation of state. So now comes the mathematical model. On the right hand side, we can see the lattice-Boltzmann governing equation, in which Fi is the particle distribution function in a given direction I. Si is the forcing term. On the left hand side, figure 6.1 shows the flowchart for the lattice-Boltzmann algorithm, where first step is initialization of domain for fluid flow simulation. Then in next step, interaction forces are calculated, and in the next step, equilibrium distribution functions are calculated, and in the next two steps, collision and streaming steps are carried out. The next step is boundary condition. So boundary conditions are applied, such as periodic boundary condition or bounce back boundary condition, as shown in figure 6.2 and 6.3 respectively. After that, the fluid macroscopic properties such as density, velocities are calculated with the help of particle distribution function f. And lastly, solution convergence is checked. If the solution is not converged, the algorithm repeats the steps from force calculation until the solution is converged. Now comes the validation part. So the static droplet is simulated in a 2D domain with the liquid droplet at the center of the 2D domain, and it is surrounded by its vapor density, and by varying the radius of droplet corresponding to that, pressure difference between the phases is calculated and plotted as shown in figure 7.2. So E4, E6 and E8 order of isotropy is considered in this simulation for calculating the interaction forces, and the relation of pressure difference with respect to the radius of liquid droplet is same, and this the slope gives the interfacial tension values, and this validates the Young-Laplace equation. Then contact angle measurement is done using spherical cap method. So in this simulation, a droplet is initially defined near the bottom wall of 2D domain, where left-right boundaries are periodic and top or bottom boundaries are boss with some fictitious density that is adjusted with the help of a parameter beta, and the fictitious density ranges from the vapor density to the liquid density. So this is the animation for fluid solid interaction for different values of beta, also shown in table 15.1, and the results are compared with those of Huang and Liu 2009. So now comes the result. So figure 13.1 shows the maximum magnitude of express current denoted by Vmax versus reduced temperature T by Tc. A plot for all the three cubic equation of state, that is CS, Carnan-Stirling, PR, Peng-Robinson, and RK, Rodman-Keller equation of state, considering fourth, sixth, and eighth order of isotropy. So in all the three plots, for a higher value of reduced temperature, say near 0.9, 0.85 reduced temperature, for each equation of state, the maximum magnitude of express current is not significant. However, as the value of reduced temperature decreases, so for each equation of state, one can notice that the Vmax value, or the maximum magnitude of express current value, becomes significant, as well as varies with higher rate. So for figure A, that is for CS equation of state, this equation of state can be used for quite low reduced temperature as compared to PR equation of state and RK equation of state for multiphase fluid flow simulation due to lower magnitude of spurious current, thus providing higher numerical stability. Also, the maximum magnitude of spurious current for 8th order of isotropy, that is represented by the black curve, becomes dominant over the other spurious current values for 4th and 6th order of isotropy at reduced temperature that is below 0.6, and this temperature for PR equation of state is around 0.71, so less than that. The spurious current values become dominant for 8th order of isotropy as compared to the values obtained from 4th and 6th order of isotropy. However, for RK equation of state, the maximum magnitude of spurious current for using 8th order of isotropy comes out to be the least among all the 3 order of isotropy, and the trend is the same throughout the reduced temperature range. So this slide shows the comparison of spurious currents magnitude among all the 3 cubic equation of state using 4th, 6th, and 8th order of isotropy. So each figure shows the maximum magnitude of spurious current versus reduced temperature while using 4th, 6th, or 8th order of isotropy. So for figure A, that is for 4th order of isotropy, on x-axis we have reduced temperature. On the vertical axis we have maximum magnitude of spurious current. So at a higher value of reduced temperature, the spurious current's magnitude is largest for RK equation of state and smallest for CS equation of state. As you can see, that blue color line is for RK equation of state and yellow color line is for CS equation of state. However, this behavior is slightly changed, and we can see that as the reduced temperature is further reduced, so at around 0.75 reduced temperature, the spurious current magnitude is dominant for PR equation of state, and still the reduced the spurious current value for CS equation of state is the least among all the 3 equation of state. And similar trend is observed for a higher order of isotropy, that is for 6th and 8th order of isotropy. And this change in the trend of PR equation of state being becoming dominant in terms of spurious current So the value of reduced temperature is still somewhat near the value of 0.76 or 0.75. So what we can observe from all these three figures is that the CS equation of the state provides the smallest value for maximum magnitude of spurious current among all the three equations of state. So thus we can say that CS equation of state is the most stable equation of state in terms of the spurious current magnitude. Lastly, multi-component multi-phase separation simulation is performed. Here is the animation for the same. So we can see three different colors. So each color represents a different component of fluid. And on the left hand side, figure 515.1 shows the time evolution of phase separation of these three components at different time steps. These are the conclusions from the comparative study, which were also discussed in the previous slides in the results section. Here we can see the reduced temperature ranges for each equation of state, for which the maximum magnitude of spurious current is highest for a given order of isotropy. Among all the three equations of state, CS equation of state is found to be useful for fluid simulation for relatively lower reduced temperature of up to 0.6 for all the three order of isotropy without concerning for numerical instability due to spurious currents. Lastly, multi-component multi-phase LB simulation is carried out and qualitative results are shown for phase separation dynamics in 2D. This is the bibliography. Thank you.
Thank you. Thank you very much for this nice presentation. Thank you. Thank you, Mohit Kosan. Now I am requesting audience, if you have any question, you may ask, please. Okay, so I think audience does not have any questions, so I am requesting volunteer, please. Now this session is, I think, completed. What should I do?
Yes, sir. Yes, sir. I thank you for Professor Suman Ghosh for chairing the session. Thank you, sir.
Thank you.
And thank you to all the participants for joining in. The next session will start from 11 a.m. I would request you all to join, please. Thank you.
Thank you. Can I leave? Can I leave?
Yes, sir.
Okay, thank you.
Thank you, sir.
Thank you.
yeux est trop grand pour comprendre des choses aussi petites.
Vous allez l'écrire à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
Hello.
Yes.
Am I audible? Am I audible,
Yes.
madam?
Yes, you are audible.
Okay, madam.
Good morning. Welcome all. This session will be chaired by Professor. Hello. Good morning, ma'am.
Good morning.
Welcome all. This session will be chaired by Professor Vanni Ray from IIT Delhi. Welcome, ma'am. Over to you.
Yeah, thank you. Good morning, everyone. So this is towards the end of the conference. We are having this session, and today's session, as I say, is mainly on the application of heat transfer and fluid mechanics. So there is a range of papers and presentations starting from solar systems to boiling to refrigeration. So I hope it will be an interesting session. So the first talk today will be from IIT Roorkee. The title is Experimental Investigation of Adiabatic Straight Capillary Tubes for Mass Flow Rate for Partially Condensed R32. So the presenter is Mahesh Bhai Banazara, I guess. So you could start the presentation. Thank you.
Namaste, respected sir. I am presenting my paper in 8th International and 47th National Conference on Fluid Mechanics and Fluid Power at IIT Guwahati, India. The title of my paper is Experimental Investigation of Adiabatic Straight Capillary Tubes for Mass Flow Rate for Partially Condensed R32. My paper number is FMFP 2020-252. Authors are myself, Mahesh Punjara, and my guides, Ravi Kumar sir and Anil Kumar sir. We are from the Department of Mechanical and Industrial Engineering at Roorkee, Uttarakhand, India. This is the abstract of the paper. This paper presents the experimental investigation of mass flow rate for partially condensed refrigerant R32 for an adiabatic straight capillary tubes. Test sections are made from a combination of capillary length and diameter. Diameters of the capillary tubes are taken from 1.12 mm, 1.27 mm, and 1.15 mm, and the capillary lengths are taken from 1000 mm, 1500 mm, and 2000 mm. A capillary tube is also tested for different inlet pressure. The mass flow rate of refrigerant R32 for different inlet pressure and quality are tested at the inlet of the capillary tube. The data of variation of mass flow rates are taken for all the test sections. A plot of mass flow rate versus various parameters like drainage friction, capillary tube length, valve-body ratio, and diameters are plotted. The schematic diagram of experimental setup is as shown in figure. The number of components are listed and given the numbers, and that numbers is indicated in the figure. This is a basically vapor compression refrigeration system. Vapor from the evaporators enters into the compressor where it compresses, and high pressure vapor enters into the condenser through the oil separator. In condenser, it gets condensed, and that is to be received in the receiver. After the receiver, it enters into the dry and filter. After the dry and filter, there are two circuits in this diagram. One circuit is directly coming into the evaporator tank inlet through the hand-operated expansor valve. And another circuit is using test section of the capillary tube, that is indicated as number 16. And before that, it requires some treatment. So that second circuit is using Corliss flow meter to measure the mass flow rate of the refrigerant that is entered into the test section. And the special treatments is to control the quality of the refrigerant is given with the help of subcooler and the preheater. So subcooler and preheater are used to control the quality of the refrigerant that would like to enter into the inlet of the capillary tube test section. Before they enter into the capillary tube test section, one view glass is provided to see the conditions of the refrigerant entering into the test section. At the both end of the test section, pressure gauges are mounted to get the pressure at the inlet and outlet of the test section. After the capillary tube test section, that line is also merged with this other line at the inlet of the evaporator tank. And from the evaporator tank, the circuit is repeated through this compressor. Geometry and operating parameter of the capillary tubes are as per shown in the table. The test sections are made by the combination of diameter and the length. So first we have to take the diameter of the capillary tube 1.12 mm, and by taking three different lengths 1000, 1500 and 2000, we have made three test sections. After that we have taken another capillary with the diameter of 1.37 mm, and we have also taken three different lengths of that capillary. By this way, we can make total 9 test sections of the capillary tube, and that all 9 test sections are operated for 3 different inlet pressure that are 1586 kilopascal and 1724 kilopascal, with the range of quality of the refrigerant varying from 0.05 to 0.27. Figure 1a represents the mass flow rate versus capillary tube diameter for the different inlet pressure with different capillary lengths. From the plot, it can be observed that when the diameter of the capillary tube increases, the mass flow rate increases for all the inlet pressures. Figure 1b indicates the mass flow rate versus capillary tube length for capillary tube length 1000 mm, 1500 mm and 2000 mm. For all the three pressures, it can be observed that the mass flow rate will be maximum for the higher pressure and lower length of the capillary tube. Figure 3 shows the variation of mass flow rate with inlet refrigerant quality for capillary diameter and capillary lengths. The effect of mass flow rate versus drainage fraction for the inlet pressure 1724 kilopascal for constant length and different capillary diameter are shown. From this graph, it can be observed that the mass flow rate will be higher for the larger capillary tube diameter. Also, by increasing the drainage fraction, the mass flow rate can be reduced. Figure 4a shows the variation of the mass flow rate versus L by D ratio, that is geometric ratio, of the capillary tube at constant inlet pressure 1724 kilopascal for different diameters. From the graph, it can be observed that the mass flow rate will be higher for the smaller capillary length and higher capillary diameter. Figure 4b shows the variation of mass flow rate versus L by D ratio of the capillary tube at constant inlet pressure 1724 kilopascal for different lengths. From the graph, it was observed that the mass flow rate will be higher for the smaller length and higher capillary tube diameter. Various conclusions from the experimental studies are listed, and that are: first, if drainage fraction increases at constant pressure, it reduces the mass flow rate of the refrigerant for all the length and diameter of the capillary tube. Second, for the constant inlet pressure and fixed length of the capillary tube, the mass flow rate for the higher diameter capillary tube was higher. Next, for the constant inlet pressure and fixed capillary length, if the drainage fraction increases for the various diameter of the capillary tube length, the mass flow rate was higher in the higher diameter of the capillary tube, and it reduces with the increase in the drainage fraction. For the geometric parameter L by D ratio of the constant pressure and fixed capillary tube diameter, the mass flow rate will decrease by increasing the length of the capillary tube. From all the experimental data, it also observed that the mass flow rate was higher for higher inlet pressure, smaller capillary length, and larger capillary tube diameter. Thanks to all of you.
Hello everyone, my name is Kiran Saikia and I am going to present.
Yeah, I have to stop it, yes. Thank you, Vanajara. So, if you have any question from the audience, we could take it first. Any question from the audience, please raise your hand. Okay, so I think we do not have, so let me ask a question. Yeah. So how are you defining the dryness fraction?
Am I audible?
Yes, you're audible. Yeah.
Madam, okay. Madam, when we are passing the refrigerant through that treatment is given as a subcooling, another is that is a PE. So after that, whatever the is given based on that, we have a fixed pressure. Based on that pressure, and by energy balance, we can calculate this much amount given, and at this much amount of heat added, whatever the condition of the refrigerant, that can be also seen from the view glass. By this way, we can calculate from the here diagram that this is the condition of the dryness fraction, mainly based on pressure.
Okay. Thank you. So, why did you choose R32 as a refrigerant? Any particular reason?
Yes, madam. Because nowadays, as we can see that R32 is having good quality as compared to the other refrigerants. It have a high capacity, and it requires small volume in the same capacity of the small capacity refrigerant system. That's why I have selected this R32 refrigerant.
Okay. Yeah, and one last question. I was just curious. I am not in the refrigeration field. So, like, what is the nobility of your work? Like the things which you said, depending on pressure and the dryness fraction and capillary geometry. So, are these things new, first time told, or something with?
Yes. There are lots of analysis carried out for this capillary tube, but they are taken with the various refrigerants. For R32, it was the first time that analysis is taken.
Okay, great. Thank you for your time. Yeah, so we'll move to the next talk today. So it's paper number 257. So the title is A Simulation Study on the Effect of Different Heating Modes on Two-Phase Flow Instability of Natural Circulation Boiling System. So it's from IIT Guwahati. So let the speaker start. Thank you.
Hello everyone, my name is Kiran Saikia and I am going to present a seminar on a simulation study on the effect of different heating modes on two-phase flow instability of natural circulation boiling systems. The overview of the presentation will be an introduction, followed by literature and objective, then modeling and validation, followed by results, discussion, and then a conclusion. Boiling is an efficient mode of heat transfer and hence adopted in various industrial applications. Like in boiling water reactors, steam is generated in the core which is then utilized to generate electricity. The Parallel Channel Natural Circulation Test Facility PCNCTF is a scaled-down model of advanced heavy water reactor which is based on the natural circulation boiling. So this is the schematic of PCNCTF. So PCNCTF consists of two loops. This is one loop, loop 1, the single channel loop. This is the loop 2, which is a parallel channel loop. So our focus is on this parallel channel loop. So in this loop, in this part, the heat is generated in the core. And steam is generated. This steam is goes to the steam drum. It is separated, and the condensed water liquid that flows through the downcomer header and is then fed back to the core. So natural circulation makes the system inherently safe, but the two-phase natural circulation has instability issues. A small perturbation of any kind can lead to high amplitude oscillation and mechanical vibrations. The oscillations may appear in different forms depending upon operating parameters, and heating power being one of the most important parameters, it determines the characteristics of instabilities. Therefore, our focus is on to determine the characteristics of instabilities on different power profiles. So these are some relevant literature on two-phase natural circulation boiling systems. And Fukuda and Kogori has categorized DWR instabilities in type 1 and type 2 experimentally. Likewise, Kumar et al. Did experiments on PCNCTF single channel systems to found out type 1 and type 1 2 oscillation. Kasar and Iyer demonstrated cold startup procedure from the parallel channel facility of the PCNCTF. In the numerical front, there are several works on the role of operating and geometric parameters on the flow instability in PCNCTF using RELAN. Liu et al. Did numerical simulation to study the characteristic of instabilities under uniform bottom peak, cosine and top peak heat fluxes in channel flow. Wang et al. Also did simulation for channel flow to study the effect of peak values, peak factor, and location. But no works have been found on the influence of non-uniform axial power profile on two-phase natural circulation instability. Similarly, very less number of works are done on the effect of unequal powers on the multi-channel natural circulation system. Therefore, we set two objectives for the present work. The first one is to analyze the influence of unequal channel power on the nature of two-phase flow instabilities of the parallel channel natural circulation system of PCNCTF using 1D thermal hydraulic code RELAP 5. And the second one is to study the stability nature under non-uniform axial power profiles like top peak cosine and bottom peak cosine power distribution. So our focus is on the three-channel parallel channel system of PCNCTF loop. So we nodalize it using this three-channel system using 1D code RELAP 5. So this is the nodalization diagram. These are core sections, risers, drum, downcomer, heater, header, and feeder. These all parts are designed as pipe components. And on the core section, you apply the heat structures to account for the input heat, and we also apply heat structure to all the components of the system to account for the heat loss. From the nodal sensitivity test, we found that 8 core nodes and 24 riser nodes are the optimum. But for the further studies, this model has to be validated, so we validated our model using the cold startup results of Kasar and Iyer and found good match with the mass flow rate data. So these are the results for the effect of different input powers on the parallel channels. So first, we plotted the simulation data results for 15% power difference between the channels, where the base power is kept at 4.6 kilowatt at channel 2, while the channel 1 gets 15% lesser power, and channel 3 gets 15% higher power. These are the corresponding values. And from the mass flow rate transient, we saw that the channel 1, the reverse flow starts at around 12,800 seconds, and it lasts till 20,000 seconds. This is the reason of the late commencement of void generation in channel 1, which can be seen from the temperature transients. Here, the core inlet temperature and core outlet temperature. The core outlet temperature suddenly becomes lower than the core inlet temperature, which signifies reverse flow in the channel and the formation of a local loop in the channel. And similarly, the pressure drop transients also shows a negative pressure drop in channel 1, signifying the reverse flow. At around 20,000 seconds, the mass flow rate of channel 1 regains its oscillatory mode, and all three channels start to oscillate together till they reaches steady state. So it can be also seen from the void fraction transients. You can see that at 20,000 seconds, the void fraction of all three channels starts to oscillate together. Similarly, for 30% pressure power difference between the channels, it is seen that the first vapor slug generates at around 9,750 seconds here, and at around 12,000 seconds, channel 1 reverse flow starts, and then again at 15,200 seconds, channel 2 reverse flow starts. This reverse flow persists till 21,400 seconds, till here. But channel 3 exhibits a forward oscillatory motion. It's seen that for both channel 1 and channel 2, the T inlet is greater than T outlet in this region. That means the local heat loop formation occurred in both channel 1 and channel 2. And the pressure drop also is negative in this region for both channel 1 and channel 2. There is significant delay of void in both channel 1 and channel 2, which can be seen from the void fraction transient. You can see that the core in channel 3, the void fraction starts much earlier at around 19,000 seconds. Secondly, we study the effect of cosine power profile. For it is seen that for bottom peak cosine power profile, the pressure rise is the highest compared to both top peak and uniform power profile. And from the mass storage transients, we see that for both top peak and bottom peak cosine profile, the gizzering starts much earlier. And also, for bottom peak power profile, the type 1 oscillation subsides much earlier than the top peak cosine profile and uniform power profile. It is also seen that there is an 8% decrease in the final steady state values of the mass storage or cosine power profile, both top peak and bottom peak. From the void fraction transient, it is seen that the void fraction generation is much less for cosine power profile, but likewise the steady state value is 17% less. Similarly, the amplitude of type 1 oscillation is much less for bottom peak cosine profile as compared to uniform power profile and also top peak cosine profile. Therefore, the primary conclusions of the present studies are: when there is a difference of input power among the parallel channels, the one with the lowest power exhibits prolonged period of reverse flow following the gizzering. It is due to the relatively lower force of buoyancy due to delayed void generation. The bottom peak cosine profile can minimize type 1 oscillation, but with the cost of steady state flow rate. However, both bottom peak and top peak cosine profile exhibit a substantial period of gizzering. Additionally, the final steady state flow rate values drop for cosine power profile. This work can be extended to a more in-depth study of power mode techniques such as various linear profiles, top peak, bottom peak, and middle peak power profile. Thank you.
Thank you, Mr. Kiran. Yes, so first I will take some questions from the audience. If they have something, please raise your hand and you can ask your question. Okay, so I think we have no questions. So let me ask one simple question again, since I am new to this topic. So you have used this software Relap 5. So how does that work? So what are the equations solved here, or what are the things solved here? 1D, as you said, it was one-dimensional
yes.
simulation. Yeah, can you just
1D transient code that use this two-fluid model, and it solves 6 different equations for two phases. It is actually used for this water vapor mixture. So it is generally used for simulating large system-wise these characteristics of mainly it is used for solving the nuclear codes.
Okay. So there are 6 equations you were saying. So what are those equations?
There are actually 6 governing equations for both phases. It's a continuity, this momentum and energy equation, and it has a it also considers the non-equilibrium, thermal non-equilibrium between the two phases.
Okay, okay. And one last question is, so the plot which you showed for the void fraction, so from that, what exact information you are getting about boiling? So is it the time at which the boiling is starting in each channel, or what exactly the information you are getting from the void fraction plots?
Madam, from void fraction plots, actually we got that since we are applying different power to the channels, so as we seen from the graph, that the one who gets the lowest power in that channel, this some reverse loop has started, and it acts as a local downcomer. So that can be demonstrated from the using the void fraction plot as well as the pressure drop and this inlet and outlet temperature plot.
Okay, okay, okay. So you have published 2 papers already on this topic, as you showed in the introduction literature?
Yes, yes, I have.
Okay, okay, great. Okay, thank you. Best wishes. Yeah. Yes, we'll go to the next paper, paper number 262. So the title is Heat Transfer Characteristics of a Modified Closed Loop Two-Phase Thermosiphon Systems. So it is from IIT Patna. And the speaker is Abhishek Singh, I guess. Okay, let's start.
Good morning to all of you. I am Dr. Manavendra Pathak, working as Associate Professor in the Department of Mechanical Engineering, IIT Patna. Today, I am going to present the topic Heat Transfer Characteristics of a Modified Closed-Loop Two-Phase Thermosiphon System. This work was done by 2 undergraduate students, Abhishek and August, as their BTech final year. Basically, a closed-loop two-phase thermosiphon system is a gravity-assisted heat dissipation device. Basic components of the loop are evaporator, riser, condenser, downcomer. In the evaporator, the working fluid at the liquid state, when it extracts the heat from the device, its phase transformation from liquid to vapor takes place. The less dense vapor rises to the riser tube and enters into the condenser, where working fluid rejects the heat and it transforms from the vapor to liquid, and it attains the high density. So the density difference between the condenser and evaporator, that produces a gravity effect, and that gravity force drives the coolant through different components. And there is no any active mechanical device like pumping in the loop. So the loop is noiseless also. We can see the closed loop two-phase thermosiphons in many applications. Thus, the heat transfer enhancement is needed for enhancing the heat transfer performance of the loop. If we increase the heat transfer rate in the evaporator, that produces more vapor and more condensate will take place in the condenser. So ultimately, gravity effects depends on the heat transfer rate at the evaporator as well as in the condenser. Few issues with the loop is dry out, which occurs at the evaporator if sufficient amount of coolants are not there or if evaporation rate is very high. Similarly, if condensation is very high, high amount of condensed liquid forms which tries to rush to the downcomer, producing a high frictional effect. In the absence of any active pumping device, the flow rate through these different components are less, so heat transfer coefficient is also low compared to any active device. Due to the dry out and the flooding problem, the critical heat flux, which is the maximum working limit of the boiling process, also low here. Then Another problem is the backflow of vapor phase. That means that vapor forms at the evaporator tries to go through this route, which obstruct the flow of condenser, and it also obstruct the gravity cycle. In order to tackle this issue, several attempts have been made, such as structured heating surfaces have been used in the evaporator to increase the heat transfer rate in the loop. Several surfaces like hydrophilic or hydrophobic surfaces have been also used. Nanofluids have been used for increasing the heat transfer rate. Similarly, non-returning valve and U-tube arrangement have been used to restrict the vapor flow from the evaporator to the down and the downcomer to restrict the vapor flow and to increase the pressure gradient from the condenser side to the evaporator and to This is the two-dimensional computational domain. This is evaporator section where initially 60% coolants are filled, that is 60% filling ratio is used. Riser tube, which in nature, then downcomer, which is adiabatic section. If we have simulated the problem for saturated boiling condition, so these are the saturation temperature and pressure. Surface tension is 0.37 Newton meter between the vapor and the liquid phase. Simulations have been made for transient condition. Volume of fluid method have been used, where time discretization has been made with explicit scheme. These are the specific time step and number of time steps in the computation. Here, schematic of experimental setup is shown. This is the evaporator section. Here, this is the both the temperature and pressure data have been collected through the data acquisition system, and high-speed camera has been used for capturing the flow structure at the evaporator. These are the specifications of the component. This is the photograph of the experimental loop, evaporator section, riser tube, condenser, downcomer, and the nozzle. Here we have presented the volume fraction distribution for the loop with nozzle and without nozzle for heat flux of 50 watt per centimeter square for a filling ratio of 60% at the time 2.1 second. We can see here, even though boiling is rigorous here in the loop without nozzle, but condensation is not very prominent as compared to the loop with nozzle. Here we can see high amount of condensation has been taken place because there is no backflow of vapor. Okay. Here we have shown the effect of applied heat flux in the vapor formation rate for two different heat flux conditions, 50 and 100 watt per centimeter square for loop with nozzle. At 50 watt per centimeter square, boiling is not rigorous and condensation is also not so high. At 100 watt per centimeter square, the boiling is high. That means buoyancy gradient is high and condensation is also high. So it actually flows the more amount of coolant through the loop, which enhances the heat transfer performance. The comparison of numerical results and experimental results are shown here. We can see here that the agreement between the numerical and the experimental results are quite high. That means our numerical prediction can produce a accurate result. This is the plot of temperature difference between heating surface and water versus applied heat flux. Here, the temperature difference between the surface and the water is high for loop without nozzle, whereas it is low for loop with nozzle. That means the heat transfer coefficient is high here with the nozzle, and in case of without nozzle it is less, because if heat transfer rate is high, that produces higher this buoyancy effect, and that increases the heat transfer coefficient, as well as that reduces the thermal rate. Here we have compared the heat transfer coefficient between these two loops. This one is for loop with nozzle, where experiments could be performed till 178.16 watt per centimeter square, which is the critical heat flux, whereas for the loop without nozzle, the maximum heat flux could be reached up to 92 watt per centimeter square only. The heat transfer coefficient is higher with the loop with nozzle. So we can see here 92% enhancement of heat transfer coefficient in loop, and CHF is this 93%. To conclude, both experimental and numerical investigations have been performed. For a loop with nozzle, the nozzle reduces the backflow and it enhances the heat transfer performance. The loop with nozzle shows 91% enhancement in the heat transfer coefficient, whereas it shows 93% enhancement in critical heat flux value. The present numerical result produces close agreement with the experimental work.
Thank you, Dr. Pathak. So the presenter was Dr. Pathak and not the other name which I said. Yeah, so first let's take question from the audience. Any question, please raise your hand and you can ask your question. Okay, so let me ask then. So the question which is arising after I saw your talk is about this nozzle geometry. So how did you decide the nozzle geometry in your experiment as well as in numerical? Yeah, you have to unmute Dr. Pathak. You can see him. Are you there, Dr. Manamendra Pathak? Okay, so I guess he is there, but he's maybe not in front of the laptop. Okay, so let's move on to the next talk. It's paper number 263. The title is Effect of Mass Flow Rate on Bed Hydrodynamics of a Bubbling Fluidized Bed Unit. And the authors are from IIT Guwahati, NIT Arunachal Pradesh, and from Bhubaneswar. So let's start the talk.
Hello everyone, I'm Alok from NIT Arunachal Pradesh. I'm going to present my paper ID FMFP 2020-263, which is titled as Effect of Mass Flow Rate on Bed Hydrodynamics of a Bubbling Fluidized Bed Unit. Fluidization is the process by which we make a bed of solid particle to behave as a fluid. The most important feature of gas-solid fluidized bed is their temperature uniformity along with the riser. Due to its uniform temperature and rigorous mixing between solid and gas, fluidized bed can be used in fluidized bed reactor, that is chemical reactor, solid separation unit, fluid catalytic cracking to make gasoline in petroleum industry, as well as gasification and combustion of coal, biomass and municipal solid waste. Aim of our present work to investigate the bed hydrodynamics of coal in fluidized bed. And objective of this work is to understand the flow pattern of feed material within the fluidized bed as well as hydrodynamic characteristic of fluidization under different operating conditions and to calculate bed voidage and suspension density inside the riser. This is our experimental setup which is established in IIT Guwahati Fluidized Bed Laboratory. From the right hand side you can see our actual experimental setup, while on left hand side virtual representation of fluidized bed is shown. The different part of bubbling fluidized bed unit are air compressor, distributor plate, riser section and cyclone separator. The riser is made up from steel pipe having internal diameter 100 mm and external diameter 110 mm, and it is of 300 mm in height, while cyclone separator having external diameter 160 mm and barrel height is 660 mm. Mass flow rate of compressed air is regulated by gate valve and flow meter is installed to measure the mass flow rate of air. Initially, the feed material was fed from the top of the riser and then it closed, and compressed air is passes from compressor. When mass flow rate is less, the air is try to escape within the from the void, while mass flow rate increases, air try to lift the bed material, and there is a moment when all the particle is freely suspended in the air. After increasing the mass flow rate, a turbulence will create within the riser. A manometer tube is connected with each pressure tap to measure the pressure difference within the riser. Now coming to result and discussion of our research. First of all, effect of mass flow rate on bed voidage. Bed voidage can be calculated by balancing the gravity force, drag force and buoyancy force, which ends up with the result bed voidage equal to 1 minus difference of manometric water column to the density of feed material multiplied by height of two consecutive pressure tap. From the experiment, it has observed that at the lower part of riser section, bed voidage decreases with enhancement of mass flow rate, while at the upper part of the riser, bed voidage increases with mass flow rate. Bed mass flow rate is directly proportional to the pressure within the riser. So, at elevated pressure, the drag force applied on the particle increases, which results in rise in particle concentration at the upper region of riser. Now, effect of inventory on bed voidage. We found that bed voidage decreases with increase in inventory, irrespective of mass flow rate. Means for all the mass flow rate of air from 13 meter normal meter cube per hour to 32 normal meter cube per hour. This is mainly due to with increase in bed inventory, drag force required to lift the particle increases, which result in bed voidage decreases. Effect of mass flow rate on suspension density. Suspension density can be calculated by bed voidage into density of air plus 1 minus bed voidage into density of solid 720 mm above from the distributor plate, and maximum suspension density is found in inventory for all mass flow rate. The maximum suspension density was observed at a distance of 720 mm from the distributor plate for all the inventory. This trend is found due to bed voidage is observed minimum at that location. Higher mass flow rate of air and higher concentration of coal particle at higher bed inventory may be the reason due to which suspension density is maximum. From this, we have concluded that voidage of bed initially decreases, thereafter it increases with increase in mass flow rate. For 1250 gram of inventory, initially bed voidage was 0.92 which decreases to 0.82 with increase in mass flow rate from 13 to 32 meter cube per hour. Bed voidage decreases with enhancement of inventory, and minimum voidage was observed for 1250 gram of inventory, which is 0.61 at a mass flow rate of 32 meter cube per hour. Suspension density is observed to have an increasing trend with an enhancement of mass flow rate of air at riser section. At inlet of riser, minimum suspension density was 71 kg per meter cube at a mass flow rate of 13 meter cube per hour, and maximum suspension density was found 110 kg per meter cube at a mass flow rate of 32 meter cube per hour. The maximum suspension density was observed 537 kg per meter cube at a distance of 720 mm away from the distributor plate for 1250 gram of inventory at a flow rate of 32 meter cube per hour. These are some of the related work done by various authors.
Thank you for the talk. So I could see Dr. Binayak Patnaik is there from the authors list. So I guess he could answer the questions. If anybody have any question, please raise your hand and you could ask your question. So let me ask. The work which you showed for fluidized bed. So can you just tell me the novelty or the new thing which you have shown other than the previous works which people have done on fluidized bed?
Actually, this is Dr. Mahapatra, one of the co-author of this paper. Actually, this paper the work done on the atmospheric mode only. Since the pressurized mode is more compact and high heat transfer, so the measure of the work is in the pressurized bed in this paper. Mainly in this paper, we are generally dealing with higher pressure due to the dominance of pressure drag over the frictional drag, and due to which the suspension density is the major parameter which is calculated in this paper is higher. So if the major disadvantages is the atmospheric bed is that the size of the bed which you are taking, if you can increase the velocity, then the suspension density decreases, and after some time when a plant is running continuously, due to various issues in the operational power of the blower is not available to deliver the desired output of and the particles are not properly suspended in the atmospheric bed. So in the pressurized bed, we are dealing for higher suspension density calculation. This is the main novelty in this work.
Okay. So at what pressure?
Up to 1 to 4 bar.
Yes, yes, yes. And what kind of particles were used in this fluidized bed? The suspension particles?
In this particle, the particles are generally used micron. The particles delivered to that power. So
Okay. Okay. So thank you, Mr. Patnaik. Thank you.
Thank you, ma'am. Thank you, ma'am.
Srivastav. I am going to present my research on the topic fluid-to-fluid scaling of supercritical natural circulation loop under the steady-state conditions. This is the outline of today's presentation: introduction, then supercritical fluids, fluid-to-fluid scaling, literature review, numerical model, methodology, and results and discussion. Natural circulation system are those systems which is gravity driven and driving potential is obtained because of the heat source and sink. Heat source is placed below the heat sink. Potential is proportional to the density difference between the hot and cold leg and the height between the heat sink and heat source. Supercritical fluids are those fluids whose pressure is more than the critical pressure. When the temperature is less than the critical point temperature, it is highly compressible fluid. When the temperature is more than the critical point value, it behaves in a both single and two-phase manner. For every pressure, there exists temperature around which sharp property variations are obtained, which is called pseudo-critical point temperature. As you can see from the diagram, that for CO2 at 8.6 megapascal, there is a drastic variation in the properties. In supercritical state, we take advantage of these sharp variation of the property as it is similar to the two-phase system. Fluid-to-fluid scaling is an effort to obtain similar hydraulic behavior of different fluids which exist at different pressure and temperature and shows different variation of properties. The need of scaling is that it is not always possible to experimentally analyze the system whose operating conditions are very low, like in nitrogen, or very high, like in water. It is well-known phenomenon in single and two-phase system. To obtain the fluid conditions, dimensionless numbers are used, and the properties are matched in terms of non-dimensional number as well. In the recent time, the studies that has been done with the supercritical fluids involves single channel study. Here, an effort has been made to scale the model for natural circulation loop. Literature review reveals that different authors have put an effort to scale down different fluids. It also reveals that non-dimensional density and non-dimensional enthalpy are the two numbers which are important to predict the conditions for different fluids. For the comparison purpose, non-dimensional numbers like Reynolds number, Prandtl number, Nusselt number are the two important numbers. As you have seen earlier, there is a drastic variation of the properties in the pseudocritical temperature. So one cannot expect to have similar variation with the different fluids. That is why the studies that has been performed earlier with the supercritical fluids, exact behavior has not been obtained because of the different nature of variation of the properties. This is a numerical model of the present study. Different dimensions are shown in the table. CO2 is considered as a reference fluid and constant boundary conditions of temperature has been applied throughout. Resto spatial discretization technique has been used for discretization. To capture high Reynolds number phenomena, RNG capstone model has been used. 4 different models have been prepared, and it has been found when we go from model 3 to 4, there is less than 0.4% change in the relative property. So model 3 has been selected for further simulations. The present model has been validated with the previous literatures, as can be seen, and it shows that it is in a good agreement with the previous literatures. Now coming to the methodology part. As mentioned in the literature review, that non-dimensional enthalpy and density are important numbers for selection of the fluid. Similar numbers have been used in the study here as well. Considering CO2 as a reference fluid at 8.6 megapascal, it has been taken because the experimental conditions are well known. This can be scaled down in R134A and N2 at 4.4 megapascal and 4 megapascal respectively. As the CO2 is a reference fluid, a wide range of temperature has been considered and non-dimensional temperature has been found. Using this non-dimensional temperature, corresponding temperature for different fluid has been obtained for the other fluid as well, as we know all the conditions of TPC, which is pseudocritical temperature, and TCR, which is critical point temperature. Table shows the different properties of different fluids. Now this table shows the scaled temperature and which is also the boundary condition as well. CO2 temperature range has been considered from 290 to 450, which is a wide range of temperature, and correspondingly temperature for R134A and N2 has been obtained. The reason for taking these temperature range is that it covers low temperature to moderate temperature to the high temperature. The sink side temperature, it has been kept constant at 285 Kelvin for CO2, and corresponding temperature are also shown. Comparison have been made in terms of non-dimensional numbers plotted against non-dimensional temperature. One non-dimensional temperature represents one boundary condition, and non-dimensional number have been calculated considering 11 planes along the heater and taking average of all of them. As you can see, for N2, Reynolds number is highest, while for CO2 and R134A it is quite similar. The reason behind is that in the temperature range considered, the dynamic viscosity of nitrogen is less, leads to high Reynolds number. Similar variation was also obtained when friction factor was plotted with the help of Reynolds number. Figure shows the variation of Prandtl number and Nusselt number. As you can see that Prandtl number is highest for R134A, while for CO2 and N2 it is quite similar. For R134A, near pseudocritical and below pseudocritical point temperature, thermal conductivity is very less, which leads to higher Prandtl number. As Nusselt number is a function of Prandtl number and Reynolds number, the N2 was expected to have the highest Nusselt number because of the high Reynolds number in its range, while for CO2 it shows the least value. From the comparison made above, it is clear that all the three fluids does not behave exactly in the same manner, but to good consensus, as expected, because it was mentioned in the literature also that different fluids cannot behave exactly in the same manner, especially around the pseudocritical temperature. Now, the reason behind taking these three fluids is that if you want to scale down CO2 in N2 and R134A, it can be done. But as we know, the temperature condition for N2 is very difficult to achieve, nearly impossible. But we can think of in a reverse manner. If you want to analyze the system considering N2 as a fluid, then we can scale up the system in R134A and CO2. In spite of showing the least heat transfer characteristic, CO2 is still preferred as a better fluid, because for R134A, if you want to go in high temperature range, R134A is quite unstable, and the condition for CO2 is easily achievable, and CO2 is also the environment friendly in nature. Now these are the references for the present study, and thank you.
Thank you, Mr. Tanuj Srivastav. Yes, so first I will take some questions from the audience. Okay, so let me ask a question. So for the plots, as I see, the temperature versus Reynolds number, Prandtl number, everything. So there was a particular temperature at which it was maximum, and then it was decreasing on the other sides. So what actually is happening at the temperature? Can you tell the physics?
Yeah, actually, as I mentioned that for a particular pressure, there exists a temperature which is called pseudo-critical temperature, where the sharp variation is obtained. So that particular, if we operate our system in that particular range, then we will have a enhanced thermophysical properties. But as we cross that pseudo-critical point temperature, as you've seen that in the diagram, that Cp attains a maximum, but after that there is a sharp decrement. So that sharp decrement is because of the loop, the average temperature has crossed the pseudo-critical point. And for the supercritical fluids, this is the advantageous thing if we try to operate within that range only.
Okay. And like the friction factor formula which you used with Reynolds number, was it a standard formula you used? Or?
Yeah, I took it from the literatures.
Okay. And the validation which you showed, actually it was not clear. So it was an experimental result with which you validated?
Yeah, it was experimental.
Okay. Thank you, Mr. Sivas. Thank you for your talk. Yes, we'll go to the next talk, and which is the last talk of the session. So experimental study of a nanofluid based solar thermal system for district heating application. So it's from IIT Roper and Pune, so College of Engineering, Pune. So let's start the talk.
Greetings of the day. I'm Vismay Kulkarni from the Department of Mechanical Engineering, Indian Institute of Technology, Roper. I am the first author of the paper titled Experimental Study of Nanofluid-Based Solar Thermal System for District Heating Applications, along with Vishal Palla, Kapilkar and Himanshu Tyagi as the co-authors. Dr. Himanshu Tyagi is also the corresponding author of this paper. I, on behalf of all the co-authors, will be delivering the presentation. So, to begin with, let's first have a look at the concept of district heating systems. These systems supply hot water and fulfill the space heating requirements using a network of insulated pipes. The district heating systems can be local to a group of buildings, single neighborhood, or span entire cities. The heat is usually produced in a central facility, which is often a fossil fuel fired combined heat and power plant. About 84% of the energy demand for the district heating are covered by fossil fuels. However, with the advancement in the district heating system, renewable sources of energy such as solar, geothermal, and biomass are being integrated into the existing systems. A simple schematic of the district heating system is as shown in the animation below. The hot water at around 90 to 95 degrees Celsius is produced at the central facility, which is supplied to a group of buildings to fulfill the hot water and space heating requirement with the help of additional accessories such as heat exchangers. The returned cold water is supplied back at around 65 to 70 degrees Celsius to the central facilities, and the cycle is continued. Let's have a look at the various generations of the district heating system. The first generation district heating system used steam as a heat carrier. This system utilized individual boilers in the apartment building. This system hugely depended on fossil fuels to produce steam in the boilers and faced huge distribution losses. The second generation district heating system used pressurized hot water as a heat carrier. The motivation behind this was to achieve fuel saving and reduce the heat losses. This system also utilized the heat from the combined heat and power plant. The third generation district heating system used pressurized hot water with a supply temperature below 100 degrees Celsius to further reduce the heat losses. This system still depended on the fossil fuels to fulfill the district heating demand. With the increasing demand for district heating and dependency on the fossil fuels gave rise to environmental impact such as rise in the global temperature and climate change. Hence, the focus started shifting to integrate renewable sources of energy into the district heating system. The fourth generation district heating system utilized hot water at a temperature of around 30 to 70 degrees Celsius to further reduce the distribution losses, and it integrated renewable energy sources into the existing district heating system. Further ahead, to reduce the dependency on fossil fuels and integrate more amount of renewable energy through fifth generation district heating system was introduced, which utilized hot water with a supply temperature close to the ground temperature to reduce the distribution losses. The schematic of fifth generation district heating and cooling system is as shown in the figure. The network is balanced throughout the year, which is bidirectional, decentralized, and it employs a closed loop. Any residual heat or cold demand is further met with renewable sources. The storage facilities act as a buffer to bridge the temporal gaps between demand and supply. Out of the various renewable sources that can be used for the application of district heating, the solar energy stands out as one of a reliable and promising candidate. To further elaborate, the solar energy incident on the Earth's surface, even for 1 hour, is sufficient to fulfill the total energy consumption of the entire world. Conventionally, to harness solar energy, the flat plate collectors, that is the surface-based absorption system, are widely used. However, these systems face shortcomings such as high energy losses, thermal resistance, and distortion of the selective coating with high incident flux. Further, the working fluid employed in the flat plate collectors is almost transparent to the incident solar radiation. Recent studies have found that the nanofluids enhance the performance and also minimize the losses, wherein the incident radiation is absorbed directly by the nanoparticles and then distributed more uniformly to the working fluid. Such systems are referred to as volumetric absorption systems. In the present research work, the objective is to investigate the merit of nanofluid-based volumetric absorption system, referred to as VAS, over the surface-based absorption system, referred to as SAS, for the application of district heating. Further, we aim to determine the impact of nanoparticle concentration and the volumetric flow rate on the outlet temperature of the solar collector. The motivation is also to find the optimum nanoparticle concentration and optimum volumetric flow rate in case of VAS and SAS. Later on, the aim is to determine the influence of distance between the light source and the spiral collector on the performance of both VAS and SAS. Now, let's have a look at the experimental arrangement of our study. As shown in figure, the light source is placed at a distance of h from the solar collector. The light source irradiates the working fluid flowing through the spiral collector. The glass cover has been placed over the collector, which helps in eliminating the heat losses to the surrounding. The spiral collector is fabricated from a bakelite with a thickness of 2 mm, depth 8 mm, and length 350 mm. The syringe pump facilitates the flow of working fluid through the collector. The working fluid enters at the center of spiral collector, travels around the circumferential path in an anti-clockwise direction, and then exits at the end of the spiral collector. The working fluid employed is a homogeneous mixture of amorphous carbon nanoparticles with distilled water as a working fluid, whereas in case of SAS system, only distilled water is used as a working fluid. In order to measure inlet, outlet, and ambient temperature, 3 K-type thermocouples are employed. Each experimental study has been conducted 4 times to ensure repeatability, and the results obtained were observed to be within statistical tolerance limit of 95% confidence interval. Now, we present the results of the experimental study. The primary objective of the study is to determine the optimum nanoparticle concentration in case of VAS. It is a concentration at which the maximum temperature rise is achieved. In order to find the optimum nanoparticle concentration, the experiments were conducted keeping the volumetric flow rate as 50 ml per hour and the value of H equal to 150 mm. The value of nanoparticle concentration was varied from 20 mg per liter to 100 mg per liter. As shown in the figure, the maximum temperature rise of 8.7 degrees Celsius is obtained at the concentration of 60 mg per liter, which is the optimum nanoparticle concentration. For all other nanoparticles concentration, the temperature rise obtained is lower than that at the optimum nanoparticle concentration. This is because initially as we increase the nanoparticle concentration, the absorptivity increases. It reaches the maximum value at 60 mg per liter. But with further increase in the nanoparticle concentration, the maximum amount of solar radiation is attenuated only in the top layers. The incident radiation is not able to reach the bottom layers, and hence the average temperature rise obtained decreases. Further, to investigate the effect of volumetric flow rate on the temperature rise of nanofluid-based volumetric absorption system, the volumetric flow rate was varied from 25 milliliter per hour to 200 milliliter per hour. The experiments were conducted with the obtained optimum nanoparticle concentration, which is 16 milligram per liter, and the value of H was equal to 150 mm. The maximum temperature rise of 8.85 degrees Celsius was obtained at the volumetric flow rate of 25 milliliter per hour, as shown in the figure. It was observed that as the volumetric flow rate increases, the temperature rise obtained decreases. This is because the duration for which the nanofluid remains in the incident radiation decreases with increase in the volumetric flow rate, and hence the temperature rise obtained decreases. Now, we determine the optimum volumetric flow rate in case of SS. It is the volumetric flow rate at which maximum temperature rise is obtained. The experiments were conducted by keeping the value of H equal to 150 ml and using distilled water as the working fluid. As shown in figure, the optimum volumetric flow rate is obtained at 100 milliliter per hour, where maximum temperature rise of 8.4 degrees Celsius is obtained. This is because for volumetric flow rate of 100 milliliter per hour, the same working fluid is able to traverse the entire length of the spiral channel, which is not possible for lower volumetric flow rate of 25 and 50 milliliter per hour. Whereas as we increase the volumetric flow rate beyond 100 milliliter per hour, the duration for which the fluid portion stays in contact with the selective surface decreases, and hence the temperature rise obtained decreases. In order to assess the merit of VS for the purpose of district heating, performance of both VS and SS are compared for various values of H. The value of H is varied from 120 to 210 mm. The experiments are conducted with obtained optimum nanoparticle concentration and volumetric flow rate in case of VS and SS respectively. As shown in figure, the temperature rise obtained increases with decrease in the value of H for both SS and VS. This is because as we decrease the value of H, the incident radiation increases, and hence the temperature rise obtained increases. Temperature rise obtained is higher with VS as compared to SS for values of H equal to 150, 180 and 210 mm. Increase in temperature rise of about 7.2% higher is achieved in VS as compared to SS for the value of H equal to 210 mm. Now, to summarize the results, the optimum nanoparticle concentration and optimum volumetric flow rate is obtained at 60 mg per liter and 100 ml per hour for VS and SS. Maximum temperature rise of 8.85 degrees Celsius is obtained at volumetric flow rate of 25 ml per hour for VS. On comparing the performance of both VS and SS, the temperature rise of about 7.2% higher is obtained in VS as compared to SS under similar conditions. On basis of the experimental results obtained, we conclude that the VS can outperform the SS in harnessing solar energy for the purpose of district heating. Thank you.
Thank you, Mr. Kulkarni. So I will take questions from the audience first. Please raise your hand and you could ask your question. Okay, so let me ask. So it was a great talk, as I will say. So regarding the solar power, it's really interesting that how it is changing. So I was just curious, like you took the spiral collector.
Yes,
So what was the reason for that geometry of the collector? Was it advantageous in some way?
Yes, ma'am. In the literature, am I audible first of all?
Yes, yes, yes.
In the literature, we have seen that the conventional flatbed collectors have only straight path where the fluid enters from left and it moves right. But in case of spiral, we can increase the duration for which the fluid stays under the incident radiation. And in the literature, it was found that the spiral path where the twisting of the path line takes place, it enhances the heat transfer. And so the spiral channel was used in our study to check its feasibility in heat transfer enhancement.
Okay, okay, good. And One more question, like the maximum temperature I could see you reached is close to 8 degrees centigrade. Temperature difference?
Yes, ma'am.
Yes.
It was 8.7 for the optimum
yes,
concentration.
yes. So if you want to increase it more, what change will you do in the experimental setup? If you want more temperature difference?
The incident flux has to be increased. The experimental setup was made to laboratory scale. So the incident flux, there was a limitation on the incident flux. So if we maximize the system and increase the flow path and the incident flux, we can reach higher temperatures.
Okay, great. Yes, so that's from me. So thank you, Sang, thank you again. So today's session is over and we could know so many different types of things happening regarding solar and then fluidized bed. So it was really informative session. But yes, I was missing question from the audience. That is true. So, but participants, I will say, keep on participating and do not get disheartened if you do not get questions from the audience. And best of luck for your future work. Thank you.
I thank Professor Bunny Rai for chairing the session. Thank you, ma'am.
Thank you.
And thank you to all the participants for joining. The next session will start from 1:30 p.m. It's a keynote lecture. So I would like to welcome you all for the next session. Thank you.
Vous allez discuter un instant. you.
Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
you.
Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
now strong.
Good afternoon. Hello. Good afternoon, all of you. Welcome, Professor. Hi,
Amresh.
Rajnish
Hello,
Bharadwaj.
good afternoon, Rajnish and Amresh.
Ashish is also there?
Yes.
All right. I mean, all three important persons are here. I mean, to start the talk.
Yes, so I request Professor Rajnish to start the session.
All right.
Okay, so you can wait 1 or 2 minutes, then you can start.
Sure.
Okay.
So I introduce Ashish first and then he go ahead, right?
Yeah, you are the boss.
You have one session right after that.
Yeah. First I introduce him, right?
Yes, so you can start means the introduction and you can check the presentation. If then you can start at 2 o'clock.
Sure.
Okay.
And then it will end at 2 o'clock, right?
2 or 2:05, whatever means.
Okay. And then questions and all. The next session starts at 2, right? Or what time?
The next session starts at 2 and you are the session chair, I think,
right.
in that session.
It
So if it 5 minutes, 6 minutes delayed, there will be no problem.
Sure, sure. It's a good thinking that you have put them in continuity.
Yes, yes. Thank you. Okay, bye.
Maybe I can start. It is 2 minutes, so maybe let me give a brief introduction to Ashish.
Yes, sure.
And then we can get started. Okay. So it is a live session, right? Not a recorded one.
Live session, sir.
Yeah. Okay, so the speaker for this keynote session is Dr. Ashish Kumar Sen, and it is my pleasure to introduce him. And I'm getting his introduction from the booklet of FMFP. Although he doesn't need any introduction, people know him very well. He's these days one of the favorite keynote speakers for many conferences. But anyways, he is an associate professor in Department of Mechanical Engineering at IIT Madras. He's working on wide range of problems ranging from micro, nano, biofluidics and interfaces, microfluidic technique, and also applying those to health diagnostics. And he's recipient of many awards. And this is a long list. I'll read some of them. Swarna Jayanti Fellowship and Nasi Scopus INE Award and DART Fellowship. Many awards he has. He is life member of FMFP Society as well as ISHMT. And one thing I think was missing in his introduction, that he was also faculty at IIT Guwahati. And it's good that he is back giving a seminar here. Okay, with that, I think let us welcome Dr. Sen for this exciting talk. Over to you, Ashish.
Thanks, Rajneesh. I would share my slides first. Okay. Oh, what is that I have done? Okay. My slides are visible?
Yes, they are.
Okay, so can I start?
Yes.
So good afternoon. My talk is on nature-inspired capillary flows. So capillary flows are ubiquitous in nature and daily life. When you talk about capillary flows in plants, in sponge and paper, even in animals like texas and lizard, and in fabric, even in engines. So you have the capillary flow taking place there for distributing the lubricating oil. Capillary flows are also important for space application, be it for drinking or for flow distribution in the fuel chamber. And these flows are being increasingly applied to build advanced systems such as lab-on-a-chip diagnostics, where you can see here the plasma and blood are being separated, and they are further the plasma is taken for downstream detection. So capillarity has a long history, starting from the first observation by Da Vinci to first accurate observation by Hawksby to development of the concept of surface tension by Cessna, and the inverse relationship where the capillary rise height is inversely proportional to the capillary radius by Zurin, and the explanation of the capillary rise height by Leslie, followed by the Young-Laplace equation, and then you have the contact angle from energy minimization, that was by Carl Gauss. So the series of development that has happened in capillarity. Capillary flows are well understood now, and the field is well established. You all are aware of the capillary flow is a result of the Young-Laplace pressure jump across curved meniscus and the weighting, the theta here. And we know that in the beginning of capillary flow, you have inertial regime where x is proportional to t. And then downstream, you will have the Lucas-Washburn regime where x is proportional to square root of t. And in between, you can have a visco-inertial regime. And this is Rajneesh. Hello?
I think it's fine. Go ahead.
Okay, you're able to.
Yeah.
So I just wanted to show this video. It wasn't coming up. So this is a video of capillary flow through a channel. Although the field is well established, we continue to learn from nature. As you see, this bird is trying to drink a drop of water, and the drop of water actually goes into the mouth because there is a tapered path. So people have tried to study that and develop various systems, including this work from our group, where we showed that you can transport liquid drop in a diverging slot, and you can bring in various drops and carry out processes and so on. So elastocapillary flows are more interesting. Here you have, in addition to capillary flow, you have elastic structures. Those are deformable. And here was an interesting work by Biko et al., where they showed that if you dip in a brush into a liquid, the flexible lamella in the brush would come together. And if the lamella were rigid, you will have a fixed capillary rise height that is already known from the urine. And since the lamella is flexible, you will have the liquid continue to rise, and that rise height is going to be proportional to the length of the lamella. And they could come up with this universal relation between the capillary rise height into the lamella with the elastocapillary length scale and the spacing between the lamella. And the elastocapillary length scale being a function of the elasticity of the lamellar material and the surface tension of the liquid that is trying to rise. And they could also show the relationship in terms of the number of lamella in the brush. So depending on the number of lamella, the capillary rise would also change. And the elastocapillary can also be observed based on by observing how a hummingbird takes nectar. So if you look at hummingbird's tongue closely, you see that it is not a hollow structure. You have a rod-like structure, two rods-like structure, and each of these rods is attached with a lamella. So basically it is open, as you see here. This is the lamellar structure. When the tongue is dipped completely into nectar, you will have these two lamella open. But once the tongue is being removed, I can see the air-nectar interface here. What happens is there is a surface tension gradient that across the lamella, as you can see here. The surface energy gradient is what tries to pull this lamella and form into a closed conduit. So as the hummingbird tries to remove its tongue from nectar, so you will have these closed structures formed, basically driven by the surface energy gradient. So there is a lot to learn from hummingbird. Elastocapillary has also been used for capillary origami. For example, you can take thin sheets of different materials and you can cut them into different pieces, and when you expose to a drop of liquid, you can form different structures. Okay, so that is because of the interplay between the elasticity and the surface tension of the liquid. Elastocapillary has been used to drive a liquid between two flexible sheets, and they have shown that depending on the two things, one bond number and other thing is the flexural rigidity of the sheet material, you can have various regimes. You can have a regime where the liquid just rises and there is not much deflection of the sheets. You can have the deflections of the sheet only at the bottom, or you can have the deflection of the sheets and the sheets continue to snap as the liquid tries to rise. And this was more closely studied by another group, and they showed that this capillary rise height between two flexible plates actually doesn't follow the Washburn regime. It goes as cube root of time. And further, people have also investigated that in this configuration. So they have put in these liquid drops inside a flexible structure. So this is flexible structure, but with the opening at the right. And depending on the surface property, so here you have the surface of the wall weighting, and here you have the walls as non-weighting. So depending on that, the capillary force will be different, acting differently, and the drops the structure would collapse at the right, and so the plug will continue to move. So we have done some work using elastocapillary. So this is one work we did where this is a rectangular microchannel. What you see here is a cross section of that. So you have 3 walls, the bottom wall and 2 side walls rigids, and you have the top wall which is flexible because the thickness of that is tens and hundreds of microns. So when you put in liquid, when you introduce liquid, so the liquid, because it's hydrophilic, the liquid tends to move because of the capillarity. When it does so, if you just observe close to the interface, the meniscus, you have a pressure jump, Laplace pressure jump. You have atmospheric on the right, you have subatmospheric behind the meniscus. And since this pressure here is subatmospheric, and on top of the membrane, you have atmospheric pressure, so there is a transmembrane pressure gradient. So that pressure tries to deform the membrane, and our analysis shows that the maximum deformation happens at a short distance behind the meniscus. Since it's a rectangular membrane, if you look at the YZ plane, you would see that the maximum deformation will, in fact, at a given cross section is going to be at the center of the channel. So from simple bending theory, you can get an expression for this deflection. So this deflection is important because since the membrane is deflecting, now to calculate the Young Laplace pressure jump across the meniscus, which actually is the source of the pressure that drives the flow, the deflection of the membrane becomes important because the height will change and consequently the pressure is going to change. So one can write down the expression for Young Laplace pressure jump this way, where the J star actually takes care of the deflection. It so turns out that the parameter J, which is the ratio of the capillary to mechanical restoring force, evolves as an important parameter, which consequently, as you would see, governs how the elastocapillary flow happens as compared to the conventional capillary flow if the channel was completely rigid. You can write down the Pauli law, the expression for hydrodynamic resistance, assuming is fully developed. And if you can equate the pressure gradient that is driving the capillary flow with the pressure, transmembrane pressure that is trying to deform the membrane locally around the meniscus, you can actually finally come up with this relation. So it actually relates the Washburn constant of the deformable channel compared to the rigid channel, and which is a function of S, which is a function of, again, the channel geometry, and gamma, which is a correction factor for the reduction in the flow cross-sectional area because the membrane deforms, and a dimensionless parameter J, which is again the ratio of the elastic to surface tension force. If J is greater than 0.238, then you would see that the elastocapillary flow is going to be faster compared to the capillary flow if the channel were rigid. So that is what is, so this basically qualitatively compares the capillary flow through the elastocapillary channel, the deformable channel on the right and the rigid channel on the left. And what you see here is the ratio of the Washburn constant of the deformable and rigid channels. So as you increase the aspect ratio, because the membrane deflection increases, this ratio continues to increase, and beyond a certain critical aspect ratio, there is membrane collapse. So that means the membrane becomes so pliable that it completely touches the bottom of the channel. And you can achieve almost 20% increase in the Washburn constant. And similarly, by making the channel flexible, the capillary rise height in case of a vertical channel would increase up to 40%. Used elastocapillary flow for driving liquid plug. So this is a two-tiered channel. So you have an upper channel and a lower channel separated by a membrane, a thin membrane, and you have a liquid plug which is located here. Because you have a liquid plug and the channels are weighting in nature, so the liquid plug will spread, and you have a concave meniscus on both sides, left and right. And because of that, the pressure inside the plug is going to be subatmospheric, And for that, the membrane is going to be bending upward. Now, such a plug in this configuration can be moved if you have a capillary flow occurring in the bottom channel. So if you have a driving liquid which comes in, and as we have seen, there will be a pressure jump, and the pressure here will be subatmospheric. And because of that, the membrane is going to be bent downward here locally. And when the membrane bends down, the radius of curvature here is going to increase. So R is going to increase. And that will give a pressure gradient across the plug. And that pressure gradient is going to drive the plug forward. So this is just the channel cross-section showing the two-tier channels separated by a membrane. And here's a video of the meniscus that tries to carry this plug down. If you can write the pressure gradient, which tries to bend the membrane and consequently drive this liquid in the bottom channel, and equate that with the viscous pressure loss that the plug will experience, you can come up with this theoretical relation. And you can in fact compare the experimental data that you get here with the theoretical results, and they show a very good agreement. And so we are able to move the plug a few centimeters, about 20 to 2 centimeter was the distance by which we could move the plug, which is significant if you talk about microfluidic applications. We also studied how capillary flows will interact with each other if you have a flexible membrane that is separating the two. So you have two-tier channels. You have a top channel and bottom channel, and you have the capillary flow in the bottom channel, which is coming from left to right, and the flow in the top channel, which is coming from right to left. When they are separated, when they are far away, they actually behave independent of each other, similar to what we have seen just now. So they are just flow through flexible channel with one wall flexible. But when they come close by, so the meniscus, each of these meniscus will see a diverging region, because of which the capillary flow will slow down drastically. And when they move past, they would start to see a converging section, because of which they would accelerate. So this is a video of that, and so this is the result. So you have the meniscus velocity with the distance, and as you see that when they move towards each other, so the velocity will decrease because of the Washburn regime. So the velocity decreases as with distance traveled. And when they cross each other, there is a significant reduction in the velocity. And as they move past, they will continue to accelerate. And this will happen when the J is large. That means your elastic effects are dominant. But when the membrane is rigid, if you use a very thick membrane and the J value is small, you would see that the interaction is minimal, and it almost follows the Washburn regime. So they would move independent of each other. The reduction in velocity that you see when they approach each other, so imagine this is a means of reducing the speed of capillary flow, which otherwise is very difficult. So the percentage drop in velocity when they cross each other is actually a function of the non-dimensional parameter J. And we found that the reduction in velocity is independent of where they cross. So you can introduce these two capillary flows at the same time on the left and right, or you can offset. You can wait to introduce this one while this is introduced at t equal to 0. So depending on where they would cross, that will not matter as far as the percentage drop in velocity goes when they cross each other. Recently, we have been looking at creating a conduit flow path out of a membrane. So this is a flow configuration where we have a thin membrane attached to the edge of a glass substrate. And when we introduce a liquid drop, because of the surface tension component here, the membrane actually folds and forms a closed conduit. And when it does, the liquid actually moves. So you create a channel out of a membrane. So this was studied theoretically. So we looked at the meniscus curvature at the edge of the membrane and the transmembrane pressure. And together, these actually are responsible for this capillary flow that we observe. Starting from Euler-Bernoulli, you can come up with this modified Washburn constant, and also get an expression for the profile, the bending profile of the membrane. And this was the profiles were compared between experiments and theory, and very good agreement was found for various operating conditions. And we found that the flow, even in this situation, agrees with the typical x versus square root of t regime, except at the ends when the membrane is wider enough. When the edges completely close, they touch each other, and you have a complete closed conduit where you have some sudden acceleration which is observed towards the end of when the meniscus reaches the end of the membrane. And this is something we're doing right now. So we're trying to move drops on flat surfaces, flat membranes. So when you put in a drop on flat membrane, again, because of the surface tension, the membrane would fold asymmetrically from both sides and provide a closed conduit because of which you can have these capillary flows occurring. And the membrane, if you look at from the edge, they would fold like this, like a lotus petal shape. Would observe, and depending on the width of the membrane, you will have a different kind of folding structure resulting. If you closely observe, you would see that you will have a region in the conduit which is of the order of millimeter, and then there is a portion where the membranes should come very close to each other, and the separation distance of the order of tens of hundreds of microns. So the flow region can be split into two. And this is again how the meniscus would move with time, and we see a typical L square root of t, except at the end where there is a sudden acceleration, which we think we can perhaps explain by looking at the meniscus from the side view. As you can see, as the flow progresses, at some point of time, the meniscus at the top is going to come out. So this is where this is the region where the spacing is very small, of the order of tens and hundreds micron, and this is the region where you have millimeter flow cross section. So we think that perhaps because of this, we see this sudden acceleration, which we are yet to explain. Now I would shift gear, talk a little bit about weighting of surfaces before I talk about the second part of my talk, which is about Cherius, inverse Cherius effects. So weighting, as you know, is governed by the Young's equation, and you all are aware of rough surfaces from Casey state and Wengel state governed by these equations. And you can have surfaces starting from hydrophilic, in fact, superhydrophilic to hydrophilic to hydrophobic to superhydrophobic. And superhydrophobic structures are very common in nature, and they have significant applications, starting from self-cleaning to directional weighting to water collection to slippery surface, as you see here. And they have very important applications as well, starting from self-cleaning to anti-corrosion. You will have boiling, condensation, anti-icing, and also drag reduction. So these are very important applications of such surfaces. Candle soot surfaces have been they have been for a while. This was the work which created superhydrophobic surface by exposing glass slides to candle. So you have these hierarchical nanostructures which gave rise to the superhydrophobicity. And while these structures are superhydrophobic, the problem was these are the surface is dark, they are not transparent, and the other issue was they're not very stable. So we started looking at how to get rid of these two limitations. So we took an approach as shown here. So start with a glass substrate, and you coat a layer of PDMS, and then you partially cure the PDMS so that when you candle soot, these soot particles typically they get embedded. As you imagine, you throw a tennis ball into mud, But since you are partially cured, the adhesion between these soot particles and the PDMS surface will not be very strong. So if you expose it to a water jet, the soot particles would come out, but soot particles have done their job. They have created this nano indentation, which actually gives rise to this nanoscopic roughness. So such a surface is superhydrophobic, as I would show in the subsequent slide. And if you can expose such a surface to oxygen plasma, instantly it becomes superhydrophilic. So this SiCH3 bond goes into SiCOH bond, giving rise to superhydrophilicity. But if you can heat such a surface, this superhydrophilic surface in oven at about 150 degree, these COH group actually get adsorbed into the surface. So the surface returns back to superhydrophobic surface. So this is the superhydrophobic surface with the nanostructures, and it gives a contact angle close to 160 degree, and the transparency of the surface is characterized here, which is comparable with that of PDMS. And we did various tests to see that the surface is stable, and it was tried with starting from heating with water jet to exposing to various chemicals, and they were found to be the surface was found to be stable. And as I mentioned, you can start from you can get a superhydrophobic surface this way, and you expose to plasma, you get superhydrophilicity, and you heat, you come back to the superhydrophobic surface. And this is the cycle that is shown here. And this is a composite surface. On the left, you have the transparent superhydrophobic surface, and the drop basically jumps and goes to the right, where it is superhydrophilic and spreads. Now coming back to the second part of the talk, I have about a few minutes, maybe 5 minutes, I would finish. So this is from daily life observations. When you put Cheerios in milk, they come together. Same happens when you put metal pins gently on surface of water close by, and with coins. Perhaps the same reason that you have observed the bubbles in coffee and soft drinks come close to each other. So there is an unbalanced force that is arising from the interplay of capillary, gravitational, and buoyancy effects that lead to attraction of these objects. And this was explained by Mahadevan in 2005, and there was an interesting work here that showed the reverse can also happen. That means you can have liquid drops on solid surface. They could also attract each other or repel each other depending on the thickness of the solid layer. So this is typically a deformable solid, and if the thickness is small, the drops would attract each other. If the thickness is large, they would repel each other. Liquid infused surfaces is something that we have used, so I would like to talk about. So they are found in this pitcher plant for prey capture, and they have a practical application starting from self-cleaning to anti-icing, etc. And when you place a drop of liquid on such liquid infused surface, you see this wetting ridge. So the surface, the liquid which is infused on the surface tends to rise around this liquid drop and form a wetting ridge. So what we have seen in a recent work is Cheerios to reverse Cheerios effect on liquid infused surface. So what we have here, we have a hydrophobic oleophilic surface, and we infuse the surface with a layer of oil. And when we place in 2 water drops, we see something interesting. So you place 1 water drop, and if you place the second water drop within a critical time, they would attract each other. But if you place the second water drop after the critical time, they would repel each other. And if you place these 2 drops simultaneously, they would attract each other up to a critical time, and then they would start repelling each other, which is shown here. So this is the video that I would like to show you. So if the drops are placed at the same time, that they would attract up to a critical time, and then they would start repelling each other. And if you place 1 drop and you place the second drop within that critical time, they will attract and merge. And if you place the drop after the critical time, they would repel each other. on a different kind of oil where the liquid will have less than 90 degree. In the previous case, when you see attraction and repulsion, the theta was greater than 90, but in a case where theta becomes less than 90, you only see attraction, you don't have any repulsion. So the drops would always attract each other and then they will coalesce. So this is shown in this video. So we started looking at explain why this happens and to explain. So if you have two water drops on a liquid infused surface, this is the situation shown in this schematic here. So you will have this infused liquid which is trying to form liquid rings around each of these droplets, and so the interface of the infused liquid is curved. So what happens is each of these drops would try to reach the peak height of the infused liquid, and because that is where their energy would be minimum. And from the force consideration, you will see that the force that will cause to bring them together is the capillarity force, and here gamma is the surface tension, and also buoyancy effects are accounted here. And imagine these are aqueous drops, so they would also evaporate, and the evaporation will be suppressed in between where there will be high relative humidity compared to the two sides. So the evaporation will be suppressed on these two edges and suppressed as compared to the other two edges. So you will have a lower surface tension on these two edges of the drop compared to the outer edges, and so you will have a surface tension gradient because of the evaporation effect. Now, because of the evaporation, because of the differential evaporation rate, you will also have differential temperature, because evaporation temperature is related to evaporation. So that again, the difference in the temperature arising from the differential evaporation can modify and give rise to surface tension gradient. So these two effects are considered, and this is the force because of the surface tension gradient. Now, if you can take these two forces and balance with the drag force, which is driving these drops, you can have a force balance, and you can actually predict the location of each drop with time and consequently the velocity. The liquid Rees height was confirmed by fluorescence microscopy, and the variation in the relative humidity, surface tension and temperature was also verified from experiments. And what we see was, so that this is what I was talking about, the drops would come close to each other for a theta greater than 90 case, and at some critical time they would repel each other. But when theta is less than 90 degree, they would only attract each other and coalesce. So this is the force explanation. So you'll have this is the capillary force and this is the surface tension force, and they would cross over at the critical time. So we have found that when the crossover happens, that is where the drops would change direction, so going from attraction to repulsion. But in case of theta less than 90, you will have only attraction, but then there is a force magnitude reversal happens. So because of which the drop would suddenly accelerate and come together. Same effect was also observed when you dispense oil drops on water infused hydrophilic surface, and we could see at small times they would attract each other, and at large times they would start repelling each other. I think I'm coming to the end of the slide, and with that I would like to acknowledge the contribution from my group and the funding agency. Thank you for your attention. I'll be happy to take a few questions.
I think very nice talk by Dr. Sen. Thanks a lot. Now let us have some questions from the audience. Maybe you can unmute and start asking. Somebody can hand raise, I can moderate. Okay, while people are thinking, maybe let me get started. So in the last part of your talk, you're talking of this capillary force which has a non-monotonic nature going up and down.
Yes.
But I would rather like to think that this is also a function of your film thickness which is on the surface. in the sense that if you have a very small film thickness, you may have a very different effect. This is like not universal, right?
Yeah, what we did was, the film thickness, we spun coated oil.
Right.
So, probably because of that, we didn't, it didn't result in a lot of variation in the, oil thickness. But if you can probably control the boundary or arrest the boundary, and you can dispense, thickness, which is different between experiments, probably, yes, you're right. The curvature may depend on the thickness and consequently the migration behavior. But in our case, it wasn't varied.
In fact, it happened. So I attended a talk in the Conflu this morning, and they were talking exactly like the effect of this thickness on the contact angle of the droplet and the meniscus around the contact line. So
yeah,
your regime is like more for a larger thickness, which probably they were showing like 20 micrometers. But if
right.
you go down to like 2 micrometer, you altogether will start to see a different effect. Maybe you want to explore in a follow-up paper.
Yeah, why not? But I would like to read which group was it?
I think some group in Germany.
Okay.
I can look at
Yeah,
it.
we have to see what exactly they have done. And
right. They were basically studying the evaporation with the slips.
Right.
All right. Any other question from the audience? So what about this suit, the candle suit? Is it like a durable coating? What we have found, we were trying to test something, then it is starting to coming off, this candle suit which you were explaining in the middle.
No, I think that was the science paper probably. So the surface that we have made, if I can go back there, there is no soot left there. So we have a nanostructure surface which is PDMS.
Okay.
Soot has already left. So the soot is basically the candle shooting here. So we did one earlier work where the surface was black, and there we needed the candle soot particles to make it superhydrophobic.
Okay.
But here, so that will happen when you have not partially cured it. So these soot particles will be very strongly adhering to the surface. So even with water jet, they won't come out.
Really? Okay.
But yes, so I mean, it's not very easy to take them out. But here, you have partial curing that has happened. Okay, so the adhesion between the soot particles and the surface is not very strong. So if you just wash in water, they are going to come out. But what they have done is they have created these dimples. So these nano dimples on the surface. So which is PDMS. So there is, but again, there is a balance between how much you cure here. If you cure here too much, then during candle shooting, you don't get any nanostructure because it's completely solid. If you cure too little, the problem is the soot particles get adhered very strongly and they don't come out. Okay. So there has to be a right duration and temperature at which you cure so that they embed enough to give you nanostructure, but then they come out easily.
Okay. I think we mixed the curing part. Anyway, we were doing out of curiosity.
Yeah.
My last question is regarding, you were showing a capillary rise and that was not following the Washburn law, which was a cube root of the time, right?
Yes.
In one slide. So what is happening there? I think missed it.
Yeah, again, I mean, we have to see the paper, but what really is when so these are two flat plates, okay, and you are dipping one end into the liquid, and because the structures are flexible, and you have capillary pressure, so each plate tries to bend. So when they try to bend, they would bend more at the middle than at the edges.
Okay.
And so because of that, the flow cross section is different. And flow cross section is different, and then you have elasticity also coming into picture.
Right.
And together, perhaps they are giving rise to a regime which is very different from Washburn. In fact, for our channel flexible channel case, we also saw an Washburn expression which is different as compared to the typical Washburn. So when you have elasticity coming into picture, they can alter the typical, visco-inertial, because you have visco-inertial and then elastic.
Right. In fact, I have seen a couple of papers where they are drying droplets on membranes, and because of deformation, the evaporation is different.
Yes.
Some groups in Germany have done that.
Yes.
All right, I don't have any more question. Any question from audience? All right, if there are not many questions, I think let us thank Dr. Sen again for his a very impressive talk. Okay, and then we can start the next session, which is on the bio-inspired fluid mechanics.
Thank you.
Thank you, Ashish. Thank you.
Thanks. I will stop sharing. And
sure.
Hello, sir.
Yes, we can start session 9D now. I think you can take care of that.
Okay.
So take care on the playing the videos, right?
Yes, sir.
Yes. So the first talk, I have the numbers, so we can just go directly putting the videos. So this session is on bio-inspired fluid mechanics. We have around 7 talks today, and the first talk is paper 51, and let us start with that. Who is the speaker? Are they present? Okay, it's my student. Sarvesh, are you around?
Yes, sir.
Okay, Sarvesh is there, the speaker. Let us see the talk what he has to say. Thank you.
Welcome to 8th International and 47th National Conference on Fluid Mechanics and Fluid Power. My name is Sarvesh Shukla. I will present my work on computational study of propulsive performance analysis of traveling wave on the surface of a foil. To explain why did I choose this problem, I will move to the next slide to discuss my motivation for this problem. As we know that fishes have a very efficient locomotion mechanism, which has been evolved through biological selection process. In his book, Hertel showed in 1966 that dolphins have a wave on its surface while catching its prey or moving forward. We can see the waves on the surface of the dolphins. This motivated me to pose different questions. How does this wave generate thrust for propulsion? Why do all fishes not show this kind of motion for propulsion? What will be the flow dynamics around the body? What will be the acoustics around the body? What other parameters will affect this motion? And how will these parameters will influence the thrust? I will try to answer some of these questions in this presentation. Relating to traveling wave, lot of works has been done. I will present some of them with main focus on surface traveling wave. First one is an experimental study by Taneda and Tomanari. They have performed an experiment for varying amplitude traveling wave over a plate. This plate is placed in a fluid domain with constant influx. They made qualitative observation about how the flow is influenced around the plate with traveling wave. In second paper here, Wu and others have done a computational study where a cylinder with a traveling wave at the leeward side is placed in the fluid inflow. In this, they found that the reverse vortex Kármán street can be eliminated with this leeward side traveling wave, and they have found that 85% of drag coefficient is reduced. They have also said that this traveling wave on the surface can be used to generate thrust. In other paper, Tian and others have studied a self-propelled motion due to traveling wave on the surface of a foil. Tian has also compared the undulation with traveling wave motion. They have found that the final mean cruising velocity are 0.58 c for undulatory body and for 0.52 c for traveling wave, where c is the phase velocity. So the research gap that we found is that how the thrust vary with the different characteristic of wave and what is the mechanism of thrust generation. So to solve our problem, we have used an in-house solver which is based on immerse boundary method. The fluid solver uses finite volume method with fully implicit pressure projection method on collocated grid. To capture the boundary, level set function is used along with minimum distance and winding algorithm. This code is verified for different benchmark problem by our research mate Namshad, but I have also verified this code for a small amplitude wave. Here I have used a problem where leeward side of cylinder has a traveling wave for Reynolds number 500. This problem is taken from Wu and others 2007 JFM paper. The curve here shows the result matches with the published data. In the present problem, a traveling wave over a surface of NACA 0012 foil is considered with traveling wave equation as shown in the slide, where y is not present the profile of hydrofoil. We can see that the amplitude is a function of profile of the foil. In this problem, tethered motion has been considered, that is the body is stored in the fluid domain. Based on the non-dimensional equation, 4 fluid parameters have been selected. First one is the Reynolds number based on the chord length. Second one is the velocity ratio, which is a ratio of wave speed to the free stream velocity. Third one is the wave number, and fourth one is the non-dimensional amplitude of wave, which is the ratio of local traveling wave amplitude to the local half thickness of foil. The value for parameters are shown in this table, where Reynolds number is fixed at 5000 with for all velocity ratio from 0.1 to 10 with fixed AM 0.3 and K is equal to 10. The grid in the fluid domain is heterogeneous. It has a very fine grid near the foil and coarse grid very far from it. The hyperbolic tangent function is used for stretching from fine to coarse grid. After grid independence test, as shown in figure, it is found that the desired finest grid size near body is 0.001. Now we will discuss the flow dynamics around the foil. Here the velocity vector is plotted along with the u velocity contour. The upper two contours show the case for velocity ratio less than 1 and the lower two show for velocity ratio greater than 1. From these vectors we can see that there is a burgeoning of velocity profile near trough for velocity ratio greater than 1 case. This is plotted as a line diagram in here to show it clearly. This burgeoning is attributed to the formation of localized jet in the trough of the wave. We can see that at the crest here is a flow reversal. From the contour, we can see that there is a high velocity as well as high pressure at the trough. There is a low pressure at the crest which contributed to the reversal of the flow at the crest as discussed before. The low pressure at the crest is due to the downward motion of the crest point, which will create a suction, and at the trough the wave pushes the fluid in upward direction, which creates high pressure region in the trough. So the thrust generation is mainly attributed to the localized high velocity jet and high pressure region at the trough of the wave. It can be seen that the almost no wake is found behind the body. The fluid region affected by the motion is very less, which makes it useful for stealth motion in fishes to catch their prey. This is a plot for time average coefficient of thrust with different velocity ratio. As we increase velocity ratio, coefficient of thrust increases and propulsive efficiency reaches its plateau near velocity ratio is equal to 5. We have plotted the two components of coefficient of thrust, the pressure component and the viscous component. The pressure component increases monotonically with increasing velocity ratio, while viscous component decreases monotonically. The mean thrust becomes 0 at velocity ratio is equal to 1.2. That means as we increase velocity ratio from there, we will get thrust 4. To analyze further, we have divided the whole foil into zones based on the wave number. As here wave number is 10, so here are 10 zones. We have found that there is a drag for zone 1 because of the stagnation point in this zone. The maximum mean coefficient of thrust appears in zone 4, which has a maximum amplitude, as the maximum amplitude of NACA 0012 is at 30% of the chord length. The mean coefficient of thrust becomes constant for zone 6 to 9, while for zone 10 it increases again due to the advection of the jet in the previous zones. We have changed the phase difference between upper and lower surface wave. We have found that the mean thrust coefficient increases while the RMS value of lift coefficient decreases with the phase angle phi increasing from 0 degree to 180 degree. So to check how the coefficient of thrust increases, we have plotted upper and lower layer drag coefficient for different phase. The dotted line shows the lower surface drag coefficient while solid line shows for upper surface. Here we can see for phi is equal to 180 degree, both curves are in phase, while for phi is equal to 0 degree, they are in antiphase. So this explains why the mean thrust coefficient is high for phi is equal to 180 degree case, but the amplitude of drag coefficient curve for 0 degree is lower than the amplitude of drag coefficient curve for phi is equal to 180 degree. This is due to the decrease in the wake region with increasing phi from 0 to 180 degree as shown in the contour. The CLCT phase diagram for 15 cycles shows that for phi is equal to 180 degree case, the body is laterally stable due to less variation in coefficient of lift, which is near to 0. For phi is equal to 0 degree, the lateral stability is compromised while it is stable in the forward moving direction. So to summarize, the thrust generation in traveling wave motion is due to the localized jet formation and high pressure region at the trough. And due to absence of wake and very less disturbance area in the fluid due to this motion, it can be used as a stealth motion. The effect of phase difference in upper and lower surface shows that maximum thrust is obtained for phi is equal to 180 degree with lateral stability.
Let us have some questions for the speaker. How many grid point surveys you are having across the foil?
Actually, it is what I have taken is 1467 cross 268. So it is the grid size is 0.001 near the foil, and the course grid is 0.25. So from there to there we are using hyperbolic tangent function to change from fine grid to coarse grid.
Okay. Okay, then let us thank the speaker for the nice talk. The next talk is by a group from IIT Ropar. I think Metu Sagar is going to present, which is a numerical study of nanoparticle injection in tumors. Okay, is Metu here?
Yes, sir, I'm here.
Okay, over to you, Metu. Thank you.
Hello everyone. My topic for the presentation is numerical study of nanoparticle injection in tumors for nanoparticle assisted hyperthermia. So, what is cancer? Cancer is a disease caused due to the uncontrollable growth of cells into the surrounding tissues. The cancer statistics shows that the cancer cases are rapidly increasing worldwide. According to the estimations of World Health Organization in 2015, which shows the global map over here presenting the ranking of cancer as the leading cause of death in the different countries, and it shows in almost all of the countries the ranking of cancer lies between 1 to 10 as the leading cause of death. Another graph over here which shows the share of population with cancer by the different age groups, which indicates that the older age group people are suffering more from cancer as compared to their younger ones. In 2018, globally, around 18 million new cancer cases were arised, in which 9.6 million were the cancer deaths. And the Asian countries share the maximum number of cases for both the incidence and the mortality rates, followed by the European and the American countries. And in India, the total number of cases were near around the 6 lakhs for both the males and the females. And in the total cases of the males, the major cancer types were of the lip and the oral cavity and the lung cancer, whereas in females, breast cancer shares the maximum percentage among all other types. For the cancer treatment, the conventional methods which are used include surgery, chemotherapy, in which the drug is given to the patients, and the radiotherapy, which uses radio frequency waves to destroy the cancer cells. Here the regimes of thermal phenomenon is shown, which shows a very less temperature of minus 40 degrees Celsius to very high temperature above the 45 degrees Celsius is used to cure the cancer. But these conventional methods are also having certain drawbacks. And the main drawback is unintentional damage to the healthy tissues. Therefore, several new techniques are under investigation to increase the efficacy of cancer treatment. And the one such technique is nanoparticle assisted hyperthermia, which uses very high temperature to destroy the tumor cells. And in this method, first the tumor is injected with the nanoparticles and then subsequently irradiated with the near infrared radiations ranging from 600 to 1300 nanometers to the targeted cells. Study shows that most of the research done on nanoparticle assisted hyperthermia considers the uniform distribution of nanoparticles. But in actual practice, this distribution is non-uniform and needs to be quantified. And the aim of this study is to evaluate the nanoparticle distribution during the nanofluid injection process. Here a schematic of tissue and tumor is shown, in which the nanoparticles are injected through the needle at the tumor center. In this study, the injection amount is chosen as 0.2 ml, which is injected with the volume flow rate of 10 microliters per minute. The spherical gold nanoparticles are chosen, which are having the diameter of 40 nanometer and are injected with the inlet concentration of 100 moles per meter cube. In actual, the porous structure of tumor is highly heterogeneous in nature, but for the present study, it is assumed homogeneous and non-deformable. The transport of the nanoparticles within the tissue and tumor is governed by the advection diffusion phenomenon, which is combined with the porous media theory for the evaluation of nanoparticle concentration. And during the nanofluid transfer within the tissues, the nanoparticles deposit on the cellular structure of tissues, and which is quantified by considering it as a concentration dependent reaction. The advection diffusion equation discussed here is slightly modified by adding an extra term which accounts for the nanoparticle deposition on the tissue surface. And this deposition of nanoparticles on the tissue surface depends upon the local fluid velocity, but for the present study, this deposition is assumed constant. And to reduce the simulation effort and time, so the simulations are performed by considering the problem as 2D axis metric along the injection axis. The governing equations which are used in this study are shown over here. The continuity and the Darcy's equation and the advection diffusion equation is used to compute the nanoparticles transfer in the tissues, and here the advection diffusion equation is modified by adding an extra term which accounts for the nanoparticles deposition on the solid structure of tissues, thereby reducing the concentration in the liquid phase. And these are the equations which are used to calculate the diffusion coefficient in the free medium and the effective diffusion coefficient by considering the tortuosity and the hydrodynamic reduction of the diffusion coefficient. Here the study parameters considered and the tissue tumor properties are shown. The main difference between the tissue and the tumor is their porosity. Tumor is having lower porosity than the tissue, and the permeability of tumor is slightly higher than that of the tissue permeability. The grid independency tests were performed to ensure the independency of the results on the number of elements. And since the primary focus of the study is to evaluate the concentration distribution, So the average concentration on the injection axis were computed for the different number of nodes. The graph over here shows after a certain number of nodes, the variation in average concentration remained very less. The free diffusion coefficient and the effective diffusion coefficient were both calculated at the body temperature of 37 degrees Celsius, and it is observed that the effective diffusion coefficient is lowered by 2 orders of magnitude as compared to the diffusion coefficient in the free medium. Here, the spatial profiles for the nanoparticle concentration distribution without the surface deposition is shown for both the tissue and the tumor at the injection volume of 0.2 ml, and not considering the surface deposition leads to almost uniform distribution for both tissue and the tumor. And for the tumor, the penetration depth is slightly higher than that of the tissue, which is due to the lower porosity of the tumor as compared to tissue. And a significant backflow is observed for both tissue and the tumor, which is due to low permeability for both. And this backflow is beneficial for spreading the nanoparticles evenly in both the cases. Here, these graphs represent the distribution of nanoparticle concentration along the injection axis without considering the surface deposition for both tissue and the tumor at the various injection volumes. And this graph shows the penetration depth increases with time as the injection volume is increased, and also, which is very clearly seen over here, is that the penetration depth for tumor is higher than that of the tissue. When the surface deposition is considered, the distribution of nanoparticles no longer remained uniform for both tissue and the tumor, which is clearly shown over here. And in case of the tumor, the penetration depth has also decreased by the slight amount than that of the no deposition case. And one more thing, the higher concentration of nanoparticles can be seen near around the injection tip, which is due to the continuous delivery of the nanofluid. Therefore, the gradient of the concentration is present mainly at the periphery for both the cases. Now, here again, the distribution of nanoparticle concentration along the injection axis is shown, but this time with surface deposition being considered at the various injection volumes. And the graph here clearly indicates that the concentration gradients are mainly present at the periphery for both tissue and the tumor. And in case of the tumor, this gradient is slightly higher than that of the tissue, which is due to the higher penetration depth when no surface deposition was considered for the tumor, which is due to the lower porosity of tumor. Finally, for a homogeneous porous structure, the nanoparticle concentration distribution remained almost uniform for both tissue and the tumor when the nanoparticle deposition on tissue surface is neglected, and also a significant backflow is observed, which is helpful for spreading the nanoparticles evenly and to avoid the concentration gradients within the tissue. But on accounting the surface deposition, the nanoparticle concentration distribution no longer remained uniform, and thereby increasing the concentration gradients. And it also reduces the penetration depth when compared to the no surface deposition case. And the injection volume which is to be delivered is to be selected depending upon the tumor shape and size. And the authors acknowledge the support provided by the Department of Biotechnology, Indian Institute of Technology Ropar, and CSIR, Central Scientific Instruments Organization.
Okay.
These are the references which are taken for the study.
Now the time for questions for Metu. Are there any questions from the audience?
What are the alternatives to gold?
As for now, the carbon nanoparticles can be considered as an alternative to gold nanoparticles, but even the most of the research which has been done in the past has considered the gold nanoparticles. But the variation which they have shown, they have not only considered the spherical shape, they have considered the gold nanorods, nanotubes. That where they have done the variations in their research. And since the gold is having very high, very good properties, so that we can cause damage to the tumor, that's why the gold is considered everywhere for destroying the tumor cells.
But how does the property of the gold come into your analysis?
Because generally the old conventional methods which are also discussed in the presentation, that they are also having the main drawback, which is that if we directly irradiate the tumor part, then the side effect is that they also damage the healthy tissues which surround that tumor part. But in case of this method, here we deliver nanoparticles only in the tumor region, and after that if we irradiate the beam, which we also have shown in the slide, it was between the range of 600 to 1300 nanometers, and in that range it does not cause any damage to the healthy tissues, but it will cause damage only to that part where that gold nanoparticles are present.
Okay.
Are there any questions? More questions for Metu?
Excuse me, sir. I have a question.
Go ahead, please.
Yes, thank you, everyone. So I want to ask that are these gold nanoparticles are being injected at the tumor site or the blood vessel some distance from the tumor site?
No, at the tumor site.
Okay, directly into the tumor.
Yes, actually there are two ways to deliver nanoparticles.
Okay.
One way is through directly into the at the spot, and one is through the veins. And for this study we have also mentioned, not in the presentation but in the slide, not slide, in the paper, full paper, that we have taken the direct injection at the tumor spot.
Okay, so direct injection, you are assuming like all the nanoparticles will adhere to this tumor site for better effectivity, right?
Yes, sir.
Okay, thank you.
Okay, so now time for the next talk, which is on the pulsatile flow, pulsatile blood flow through an stenoized coronary arteries. Okay, this is by Dr. Guwahati.
Respected judges, teachers, and friends, a very good morning to one and all. Myself, Dr. Abdul Razak Burudi, Assistant Professor in the Department of Mechanical Engineering, Nitya Meenakshi Institute of Technology, Bangalore. Today I am here to present my technical paper presentation on the topic of computational analysis of pulsatile blood flow through an idealized axis symmetric stenosed coronary artery in 8th International and 47th National Conference on Fluid Mechanics and Fluid Power, FMFP 2020. So these are the main overview of my presentation. My whole presentation includes the basic introduction about atherosclerosis and its development, blood composition and its viscosity, artery model construction, computational mesh, boundary conditions, governing equations, validation of the computational results and discussions. In result discussion, I am mainly discussing about the effect of stenosis severity on wall shear stress, effect of stenosis severity on pressure drop, effect of stenosis severity on velocity flow field, and followed by conclusions. Now let us understand first what is atherosclerosis. As we all know that atherosclerosis is also called as a coronary artery disease, which is a chronic degenerative disease and common health problem in which the thickening and hardening of the arterial wall takes place due to the buildup of fatty materials called as plaques inside the arteries. And around 7.3 million deaths every year are caused mainly due to this coronary artery disease, and despite of large impact, the actual mechanism of coronary artery disease is only partially understood,
Also, the coronary artery disease is generally due to the buildup of plaque inside the arteries that resulting in narrowing of blood vessel, which restricts the blood flow. The figure shows the hardening of arteries, how the artery becomes harder as the plaque will develop inside the arteries. And also this figure shows the development of atherosclerosis, how the atherosclerosis plaque will develop inside the blood vessels. So generally there are 5 stages in which the atherosclerosis plaque will develop inside the blood vessels. Generally the artery is made up of 3 layers, that is we can call as intima, media and adventitia. And also the endothelium is there, on which endothelium the blood is flowing. Okay, generally the atherosclerosis starts initiation due to the endothelium injury. The endothelium injury is mainly caused due to the hyperlipidemia, hypertension, cigarette smoking, etc. And as the endothelium injury takes place, then the endothelium starts dysfunction, which is not working properly. So that because of endothelium dysfunction, the monocyte, like we can call as the white blood cells adhesion and transmigration will take place. Due to the monocyte adhesion and transmigration of blood particles, the smooth muscle cells starts moving from media to intima. So that leads to the activation of macrophages inside the blood vessels. And also the fatty streaks will form as the macrophages and smooth muscle cells starts accumulating the lipid. And the 5th stage is the smooth muscle cells starts proliferate and secrete extracellular matrix starts developing inside the blood vessel. Now let us move to the blood composition and its viscosity. Generally the blood is not a single fluid, it is a multi-phase fluid which is mainly consists of the various blood particles that are mainly the plasma will be there, like plasma is the like water type liquid, red blood cells like erythrocytes, white blood cells leukocytes and platelets. Generally in total 100% of blood, the 54% of plasma will be available in the blood and 45% of red blood cells. Other than 1% it includes the white blood cells, platelets, cholesterol, lipoproteins, etc. And the figure 3 it shows the blood viscosity. So generally the blood acts at low shear rate. Generally the viscosity of the blood depends on the shear rate. As the shear rate increases, the red blood starts disaggregation, so that the blood becomes in high shear rate, the blood becomes as a Newtonian fluid, whereas at low shear rates the red blood starts aggregating and they form a Rolex nature. So we can say that at low shear rate the blood is act as a not Newtonian fluid. And this is the artery model construction. So in our present study we use idealized geometry because the reconstruction of real geometry of coronary artery is very difficult due to its internal complex structure, and also there is a difficulty in obtaining the patient specific data. So hence our present numerical study is fully based on idealized coronary artery geometry, and we created the stenosis by using the cosine function. So and we develop in this present study we use 2 types of stenosis arteries, that is 50% stenosis artery and 70% stenosis artery. And this figure shows, the figure 6 shows the idealized axisymmetric stenosed coronary artery model with the dimensions that showing the boundary conditions, various boundary conditions and the region of interest. So you can see our region of interest is this one, rectangle block, and this is our inlet zone, it is stenosis zone, and it is outlet zone. And our overall artery is having length of 180 mm and diameter is 4 mm. Now computational mesh. So the computational mesh for idealized coronary artery model is generated using ANSYS ICM CFD software, and our mesh, the mesh was generated with robust scheme, and the final mesh consists of 5,72,281 and 7,78,357 elements for 50% and 70% stenosis models respectively. And also a prism layer is used for controlling the mesh, which consists of 5 layers with a growth rate of 1.2 is employed to capture the flow near the wall. And also we carried a grid independent study to find the optimum mesh model. And also these are the boundary conditions we use for our present study. In this study, the transient pulsatile velocity profile is shown in the figure, and this transient velocity profile were used as velocity inlet boundary conditions, which is obtained from Bernie and Levy, and we use a 2 equation low Reynolds K omega turbulence model for the study. And also we carried the validation. So the computational mesh or the computer result of present study has been validated with the experimental result of Ahmad and Giddens. And for this study we use a 75% stenosis model is taken as geometry, and at inlet a parabolic velocity profile is assumed. And this figure both 11 figure A and B shows the radial velocity profiles comparison plotted at 1D and 1.5D in distal region from the stenosis throat, and we got a good agreement can be observed with the experimental values, and in spite of small discrepancies the qualitative agreement is found. And next is result discussion. The numerical analysis is performed to study the effect of stenosis severity on the blood flow behavior, and the blood flow factors like wall shear stress, pressure and velocity distributions are observed from longitudinal and transverse contours at specific times of one cardiac cycle for comparing the variation in blood flow. And the whole our observations and discussions of flow variation in both 50% and 70% stenosis arteries are categorized starting from end of diastole, that is 0.275 second, local maximum systole 0.40 second, and maximum flow at the beginning of diastole. And we simulated up to 3 cardiac cycles were simulated for each transient simulation in order to ensure the statistical convergence or periodicity, and the result analysis is done for second cardiac cycle. And this is the the effect of stenosis severity on wall shear stress. And generally we all know that the wall shear stress is a key hemodynamic descriptor which is used to determine the influence of stenosis severity. It depends on the velocity gradient and viscosity of the blood. And from the result we can say that it is significantly observed that the sudden changes in wall shear stress is mainly because of the existence of stenosis and increase in severity of stenosis. And in the whole both models 50 and 70% stenosis, the high wall shear stress is observed in stenosis and low wall shear stress is observed in the post-stenotic region of the stenosis because of the existence of low velocity and flow recirculation. This same figure, the same study of effect of stenosis severity on wall shear stress for different time step, that is 0.40 second. And also this figure shows the effect of stenosis severity on wall shear stress, which is compared for both 50% and 70% stenosis for time second 0.55 second. Now second one is the effect of stenosis severity on pressure drop, and we studied the pressure drop in both 50% and 70% stenosis, and from the result we can conclude that in 50% stenotic artery for all time steps the almost uniform pressure distribution is observed and is fluctuating with little deviation along the arterial length as comparing to 70% stenotic artery. And we also found that in the upstream region of stenosis the distribution of pressure is high and it declines suddenly at the throat, which is observed for all time steps for 70% stenosis severity model. And also the presence of stenosis in artery may lead to sudden demise of the patient by bursting the upstream region of stenosis due to having high pressure of the. And also this figure shows the effect of stenosis severity on pressure drop for time step 0.40 seconds. Same result we have obtained for both stenosis. And this figure shows the effect of stenosis severity on pressure drop, that is for time step 0.55 seconds. Now the figure shows the effect of stenosis severity on velocity flow field. So the distribution of velocity contours and its comparison for both 50% and 70% stenotic arteries at the different time step is shown in the figure. And here for all cases of 70% stenosis severity, the velocities are relatively higher than 50% stenosis at the stenosis throat and downstream region of stenosis. Also for all cases, the flow recirculation region is perceived in 70% stenosis model at downstream stenotic region and found highest velocity at maximum flow at the beginning of diastole, whereas at 50% stenosis at the end of diastole, the low velocity is perceived. And we come to the conclusion. In this numerical analysis, the transient blood flow study is performed through three-dimensional idealized stenosed coronary artery, and a comparison of pressure, wall shear stress, and velocity field contours through 50% and 70% stenosed artery at different time steps are carried out. And from the analysis of velocity and wall shear stress, it is understood that pulsatile nature of blood flow and complex stenosis geometry are responsible for the uneven plaque formation in the artery. And in both stenotic arteries, the maximum wall shear stress is observed at stenosis and its upstream region, and it increases as the stenosis severity increases. And the high wall shear stress influences plaque composition in such a way that it induces local weakening of the plaque and making plaque regions exposed to high wall shear stress that are very prone to the rupture. And also we found the low wall shear stress is observed in downstream region of stenosis due to the presence of low velocity and flow disturbance in both 50 and 70% stenotic artery. And this low wall shear stress in artery can lead to dysfunction of endothelial cells, which causes to the accumulation of new cells, subsequent plaque formation and arteriogenesis. And these are the references which we use for our references. And thank you for listening.
Thank you for the nice talk. Are there any questions? Dr. Buradi, are you there? So can I ask a question? Is the flow Newtonian or non-Newtonian in your simulations?
Sir, we consider the Newtonian flow, sir, in this study.
But in the small geometries, the blood cells may play a role and the blood flow is more like a Newtonian, non-Newtonian, right?
Yes, sir. Yes, sir. Actually, sir, generally the blood is non-Newtonian fluid only in small arteries. But in our study, we consider has diameter 4 mm. No, sir, we consider Newtonian fluid to check the results. Anyway, we did non-Newtonian also, sir. But for the conference, just have presented a Newtonian study paper results.
Okay.
That also, yes, sir.
Yeah. So let us move to the next talk by Siddharth Shankar Das from IIT Bhubaneswar, and is going to talk about blood flow in a bifurcated structures with thermal effects. Let us play the talk.
Good day everyone. My name is Siddharth Shankar Das and I am currently pursuing PhD degree in IIT Bhubaneswar under the supervision of Professor Swarup Kumar Mahapatra. My topic of presentation today will be thermal analysis of blood flow in a bifurcated structure with different plasma viscosity using multiple technology. The motivation for this study stems from the complication arise in thermal ablation therapy of tumor tissues due to the heat sink effect of blood flow. A comparison study has been done to analyze the heat transferability of blood for a normal human being and a person suffering from the HVS or for the hyperviscosity syndrome, and to show how a blood disorder affects the heat sink effect compared to normal human condition. Thermal ablation works on the principle of achieving cell necrosis by elevated tissue temperature. For exponential cell growth and division of cancer cells, it requires excessive oxygen and nutrients compared to the normal cells, which triggers the epithelial to mesenchymal transmission, or shortly called as EMT process. Now, in this process, these carcinoma cells suppress their epithelial features and change to mesenchymal ones. Because of this, a large number of blood vessels start spawning near the infected zone to provide it with excessive nutrients and oxygens. Now, during the thermal ablation therapy, while the temperature is required to raise it beyond 46 degrees Celsius, because of presence of blood vessels near it, a heat sink effect is created, which then lowers the required temperature for cell necrosis, which subsequently promotes the reoccurrence of tumor at this site. So this analysis is a comparison of the heat-sinking effect of blood for a normal human being and a person suffering from the hyperviscosity syndrome. Now, hyperviscosity syndrome is a blood disorder which is due to the excessive production of plasma protein or excessive presence of plasma protein in blood, which subsequently increases the blood viscosity compared to the normal human. Figure 2 represents the schematics of the bifurcation tree used for this analysis, which is taken from the work by Zhang and Jie. According to morphometrical investigations, the number of branches at each flow divider point in a vessel tree is almost 2. Now, tri-bifurcations are very rare, while bifurcation can be found in abundance in human circulatory system. So, a bifurcated idealized geometry is taken for this calculation. Here, X represents the length of branch vessel 1, Y represents the length of branch vessel 2. Both are 10 mm in length. Main vessel length is also taken as 10 mm. Now, diameter of the main vessel is taken as 0.7 mm and diameter of the branch vessel 1 is taken as 0.6 mm. Diameter of the branch vessel 2 was derived by applying Moore's law, which is shown here. And the angle of bifurcation here is taken as 90 degrees. At the inlet of the main vessel, a pulsatile volume flow rate is applied according to equation 1 and temperature of blood is taken as 310 Kelvin. A heat flux of 5000 watt per meter square is applied at the blood vessel wall and mostly boundary condition is also assumed at the walls. At outlet, relative pressure is taken as 0. Here, in this analysis, blood is being considered as a two-phase fluid consisting of plasma and RBC as primary and secondary phase. So, as these two combined make 99.3% of volume of blood, so the white blood cells and platelets are being ignored here as they have less than 1% volume of blood and also they don't affect the rheology of blood much. Also in the assumption section, vessel tapering and wall distensibility effect are overlooked here, and for the sake of simplicity of the study, RBC is being assumed as a spherical in shape, contrary to the discoid shape, which is in practical case. So the shape factor here is taken as 1. The three-dimensional, laminar, transient and multi-phase numerical simulations were performed using the Euler-Euler multi-phase model. Pulsatile entry and shear thinning nature of blood are incorporated with this model by the application of UDFs. As it can be seen from the equation that these equations are basic conservation equations with the exception of an extra term for volume fractions in it. In Euler-Euler multi-phase approach, the fluid, one fluid is being considered as a primary phase, which is plasma in this case, and another is being considered as a pseudo fluid or secondary phase, which is RBC in this case. And conservation equations are being solved for each one of them. In energy equation, this K and this HV represent the thermal conductivity and volumetric heat transfer coefficient for any phase K. Because of the two-phase nature of the flow, heat transfer from one phase to another also comes into the picture along with the heat transfer from the vessel wall. So Ran's and Marshall model have been utilized for the interphase heat transfer coefficient, which depends on the volume fraction of both phases and diameter of the secondary phase. As it can be seen in the right side box, the interface heat transfer coefficient is formulated like this. In our analysis, dimensionless relative mixture viscosity formulation was used to calculate the viscosity of RBCs as proposed by Ding et al., which is represented in equation 7. And the constants M and N are also represented here, which also are found by correlating the data by Ding et al. We have chosen the third cardiac cycle for our analysis to facilitate a fully developed flow for the secondary phase. As it can be seen from the figure 3, that minimum temperature variation at bifurcation is pulsatile in nature throughout the third cardiac cycle. We have taken 0.8 second as our pulse period in this analysis. There is an increase in blood temperature when plasma viscosity changes from 1 centipoise to 5 centipoise. This is due to the larger residence time of blood near the bifurcation section as the axial velocity drops in magnitude due to increase in viscosity for the same hematocrit ratio. The change of magnitude of radial velocity near the flow divider section is also responsible for an increase in blood temperature. As the viscosity of plasma increases, magnitude of radial velocity at bifurcation increases, which subsequently increases the residence time of plasma near bifurcation, also increasing the blood temperature. So, in short, as blood viscosity decreases, heat sink effect from the blood vessel wall to blood increases, lowering the temperature required for cell necrosis, which interfere with the thermal abrasion therapy. In this slide, figure A represents blood with 1 centipoise plasma viscosity as in case of normal human blood, and figure B represents the blood with 5 centipoise plasma viscosity as in case of person suffering from hyperviscosity syndrome. And the lower temperature region near the bifurcation in figure A completely disappears in figure B, representing a smaller heat sink effect. So a person or a patient suffering from hyperviscosity syndrome have a smaller chance of changing the tissue temperature compared to normal human being. Now, although the change is small in magnitude, but in case of sensitive areas like brain and ocular regions, negligence to these small magnitude changes can create severe side effects in both hypothermia and hyperthermic treatments. As it can be seen from figure 5, the transient Nusselt number varies more or less in a pulsatile manner throughout the third cardiac cycle. Also, the Nusselt number, transient Nusselt number for normal human being have a slightly higher magnitude than a person suffering from the blood disorder or HBS syndrome. Now, this also represents that a normal human being blood has a higher heat transfer capacity than compared to a person suffering from the hyperviscosity syndrome. In previous study, we have seen that transient Nusselt number for a normal human being has a slightly higher magnitude than the transient Nusselt number for a person suffering from the hyperviscosity syndrome blood disorder. Now, in here, figure 6a represents the inlet cross section of branch vessel 1 for a plasma viscosity of 1 centipoise, and the figure 6b represents the inlet cross section of branch vessel 1 for 5 centipoise. And comparing both of them, we can see that this high velocity region in the figure 6a has a higher magnitude than the figure 6b, which suggests that the normal human blood has a higher velocity or a higher axial velocity compared to the person suffering from hyperviscosity syndrome case. So this higher velocity is the primary reason for an increase in transient Nusselt number in case of normal human blood. So normal human blood has a higher chance of creating a high magnitude heat sink effect compared to the person suffering from this HBS blood disorder case. Also, we can see here that the velocity region or high velocity region, contrary to be at the center of the tube, has been shifted towards the wall. This is due to the presence of bifurcation near the flow divider inlet section. To summarize our work, it can be concluded that a normal human being and a person suffering from the HVS can be treated with the same thermal ablation therapy, but only in case of high sensitive areas like brain and ocular regions, these minimum temperature difference, small temperature difference can be taken into account. Yes, thank you.
Okay, are there any questions for Siddharth? All right, then let us move to the next talk. That is by Shahjad, and he is going to talk about latest Boltzmann modeling of cardiovascular flows. And he is also from IIT Bombay.
Hello everyone, my name is Shahjad Assam. I am going to present on latest Boltzmann modeling of cardiovascular flow in a micro channel. As we know that natural heart valves subjected to time varying stresses. This mechanical stresses changes the shape, size, function of the tissue. This is known as tissue remodeling. In contrary to this poses a great challenge for the treatment of congenital heart valve diseases in child. For example, if a child suffering from congenital disease, the heart valve has to replace with artificial one. As the child grows, we have to replace and resize the artificial heart valve, and this activity doing again and again is painful and costly. Recent studies have shown that tissue engineered heart valve has great potential for the treatment of congenital heart valve diseases, and experimentally it has been found that oscillatory shear stress play a vital role in tissue engineered heart valve. Therefore, determination of oscillatory shear stress is an important parameter, and this oscillatory shear stress can be correlated with the experimental data. So in the present study, I have developed a numerical solver for the cardiovascular flow in a microchannel using the lattice Boltzmann method and determine the oscillatory shear stress at the bottom of the microchannel at different states of time. To solve the problem, the single relaxation time lattice Boltzmann equation is used. The lattice Boltzmann equation is discretized in time and space. For two-dimensional study, D2Q9 model is used, and the microscopic properties like density and momentum density can be determined using the distribution function. For the simulation of unsteady incompressible flow, Mach number should be less than 1 and the characteristics time should be greater than length upon speed of sound. After the collision and streaming, all the distribution get updated in the computational domain except the boundary node. The unknown distribution function at the boundary can be determined by applying the boundary condition. There are several ways to apply the boundary condition. In this study, the inlet and outlet boundary condition is applied by U and A boundary condition, and the no slip at the valve is applied using the halfway bounce back method. For example, at the inlet, the density and F1, F5, F8 distribution is unknown. There are 4 unknowns, so for closing the system we need 4 equations. So one equation we can obtain using the conservation of mass, and the 2 equations we can obtain from the conservation of momentum in x direction and y direction. The additional equation we can obtain by the non-equilibrium bounce back of distribution function. so that we have 4 unknowns and 4 equations. The system is closed. We can determine the unknowns at the inlet. Similar process we can use at the outlet. The F6, F3, F7 and the outlet velocity is determined. For the validation of numerical model, a two-dimensional channel is used and Omersley flow is simulated using the lattice-Boltzmann method. And there are two different simulations conducted. In one case, analyzer pressure gauge is applied at the inlet using the two-hand gauge level condition. And in the other case, an equivalent pressure gauging circuit is applied to the channel and the periodic boundary condition is used at the inlet and outlet. So both simulation results like two-hand boundary condition and periodic boundary condition is compared with the analytical solution of Omersley flow, and it is found that there is an excellent agreement between the simulation results and NPM results. The validated numerical model is used to conduct simulation for cardiovascular flow in the microchannel. The given data is shown in the slides. Based on this data, non-dimensional number like Reynolds number and Omersley number is calculated. Using the invariant property of the non-dimensional number, NPM simulation parameter is calculated and the parameter is used to set up the lattice-Boltzmann method simulation. Under the same condition, fluent simulation is conducted and results obtained using the fluent and LVM simulation is compared with each other, and it is shown in the graph that both results are in agreement with each other. This graph shows the velocity profile at the cross section at different instant of time, and this graph shows the shear stress versus time in a given cycle. It is observed that at low flow rate, LVM simulation results are in excellent agreement with the fluent simulation. In the present study, lattice-Boltzmann method is used to simulate unsteady flow. The numerical model is validated using the analytical solution of Omersley flow. Lattice-Boltzmann simulations were performed by the two methods. In first case, the sinusoidal pressure gradient is applied at the inlet. In another case, flow is driven by the periodic body force. Results obtained by the both methods is compared with the analytical solution. It is found that there is an excellent agreement between the LBM simulation and analytical solution provided the incompressibility condition is satisfied. The model is extended for the simulation of 2D cardiovascular flow in a microchannel, and the time varying flow rate is given at the inlet. The relevant dimensionless number like Reynolds number and Omersley number of the given problems are identified. The same parameters were used to conduct the fluent simulation, and both simulation results were compared with each other. And it has been found that oscillatory shear stress and velocity profiles are in agreement with each other. In this study, it is observed that time-varying flow rate can be modeled using the single relaxation time lattice-Boltzmann method, provided the incompressibility condition is satisfied. This study will lead to further exploration of the general case of cardiovascular flow using the lattice-Boltzmann method. Thank you.
Okay. Are there any questions for Shahjad? Shahjad, you are there in this meeting?
Yes, sir. Yes, sir.
Are there any questions for Shahjad? Okay. If not, let us move to the next talk. Next talk is by Professor Sushant Datta from IIT Roorkee, and I think Vikas Sharma will present, and that is going to be an experimental study of an shear stress analysis on a bioinspired riblet surface. Let us play the talk.
Morning, all of you. Myself, Vikas Sharma, a research scholar at IIT Roorkee, working under the guidance of Professor Sushant Datta. I'm here to present my work on experimental methodology for shear stress analysis of a bio-inspired riblet surface. The presentation outline is motivation and need, concept of drag reduction, objective of the study, then the experimental methodology, then results and discussion. In the motivation need, I'll discuss from where the concept of riblet has evolved and why it is important for real life application. Then I'll explain the experimental methodology which we have used to analyze the shear drag and flow behavior over a flat surface and compare it with a riblet surface. Then we will discuss the results. The motivation of the work comes from the shark skin, which consists of different denticles, and inspired from these denticles, the concept of riblets come into existence. There are many other bio-inspired surfaces which are feasible for drag reduction, like lotus leaf, bird feather, etc. And most of the external flows, such as over ships, automobiles, and even in energy sectors, have a large amount of power requirement due to shear drag. And if we can reduce this drag, we will serve the into cost effectiveness and improvement in the energy economy. Also, there will be a saving of lot of fuel and a greener environment is possible. These microstructures, when present over the surface, alter the boundary layer phenomena and thus can contribute to a drag reduction. Normally, drag reduction can be achieved in two ways. One is by separation control and one is by reducing the wall shear stress. As we are considering only flat surfaces in this experiment, so we are not bothered about separation control. Now, most of the theories regarding drag reduction conclude to the fact that reduction in turbulence shear stress and vorticity are the main reason to reduce the near wall shear stress. As you can see in the figure, there are longitudinal vortices over a flat surface along the line of the flow. And if we can somehow have some perturbations in the buffer layer of the boundary layer, the surface drag near the wall can be altered. So the basic idea of the riblets is to have such dimension so that these near wall longitudinal vortices could not settle into the groups and will be displaced farther away from the wall, which will increase the viscous layer thickness and lead to reduction in shear stress and momentum loss near the wall. These riblets will suppress the streamwise vortex structure and it stabilize the high frequency waves. This study gives detail for controlling skin friction by the use of sawtooth shape riblet, which is fabricated using 3D printer. The riblet is analyzed for its efficacy to modify the flow in order to alter the drag behavior. Drag behavior is studied with the help of a flush mount shear stress probe. A simplified method for calibration of this probe is also explained for accurate shear stress estimation. Velocity distribution is studied with the help of a constant temperature anemometry hot wire probe. The test plates are studied in a subsonic wind tunnel for different flow behavior. The sawtooth studied in this work has an included angle of 60 degree. The experiments are performed in a subsonic wind tunnel of test section 1.5 meter and cross section 15 centimeter cross 10 centimeter. Tunnel speed is varied from 1.5 to 4.5 meter per second and force analysis as well as velocity profile development is analyzed. As the flow is not turbulent, thus inlet disturbances are used, that is roughness element and sandpaper, so that they can induce turbulence characteristic into the flow, as riblets are more effective in turbulence conditions. Sawtooth riblet is used for a length of 20 centimeter and is compared with a flat surface. As you can see in this picture, this show the mounting of the flush mount probe flush with the wall of the substrate. Above it, air flow with a certain velocity, and heat is lost by this probe due to convection. The working principle is based on the similarity between temperature and velocity profile in the viscous sublayer near the wall. Now, by the energy balance over the sensor, it can be concluded that the heat loss by convection is directly proportional to the cube root of the shear stress experienced. Now, as the voltage res- resistance of the probe is constant, thus the heat lost is directly proportional to the square of the voltage. Thus, the shear stress relation for the hot film is a modified King's law, which states that V square is equal to A tau power 1 by 3 plus B. Now, calibration is an important aspect of the study, as there is not many techniques available to measure wall shear stress experimentally accurately without obstructing the flow. Now, with the help of hot wire, we'll be calculating the velocity in the near wall region and will be estimating the shear stress experimentally, and voltage will be taken from the flush mount probe connected with the CTS setup. Now, using this voltage and shear stress calculated with the help of linear regression for different data sets, we'll be finding an equation for the calibrated flush mount probe. This figure shows the shear stress comparison for three different test plates at different speeds. Voltage is recorded from the flush mount probe, and with the help of the calibration equation, shear stress is calculated for all the cases. We can see in the figure that as speed increases, the flow becomes more turbulent and fluid interact with the probe and drag increases. The increase is not linear, as the flow has more turbulent characteristics as the speed increases. Comparing flat plate with riblet of 1 mm size, we can see that at low speed, the change in shear stress is not much. This can be because of the size of the riblet is very less to influence the flow characteristic at this low speed. But when the speed increases, the same riblets influence the boundary layer and the drag changes. If we can compare all three test plates, we can see that the test plate having 1.5 mm riblets is showing less shear stress compared to both other plates for same operating condition. Thus, we can say for the conditions tested, 1.5 mm riblet profile is suited for drag reduction. For comparison of velocity profile, we have compared flat and 1.5 mm riblet only. The two graphs show the comparison of these two test plates at different speeds in the near wall region and for the complete boundary layer development. Near wall region examines the viscous regime development of all cases, and conclusion can be made of the velocity gradient close to the wall. And in the viscous sublayer regime, drag is proportional to the velocity gradient near the wall. From the graph, it can be clearly seen that the profile of riblet surface is outside or above the curve of flat surface for all speed range tested. So we can say that there is an upward shift in the velocity profile relative to the smooth wall. Thus, the slope of the velocity profile is less in case of riblet as compared to the flat surface. So we can conclude that there are chances of less drag as well as the thickness of the viscous sublayer regime is more with help of riblet surfaces. Now coming to the second plot in which there is a comparison of complete boundary layer profile. It can be seen that the curve which was above the flat surface in first case has come outside the flat surface curve for second case. We can see it. This red which was inside is now outside. So we can say that the slope of the rivet surface has increased away from the wall and there is a better momentum exchange within the boundary layer. The reason can be the lifted vortex which was discussed in the concept of drag reduction. Thus, there is more uniformity in the velocity profile away from the wall, and the free stream velocity is achieved earlier. So, this can all contribute to decrease in boundary layer thickness, which will imply a decrease in momentum thickness as well. And this all collectively will reduce the drag of the surface. Conclusions. In this work, comparison has been made between a flat surface and a bio-inspired rivulet surface on the basis of shear force and the velocity profile development. Calibration of shear stress probe is a critical aspect of the study. The velocity analysis has shown that rivulets change the viscous regime of the flow as well as the complete boundary layer development. Thus, with the optimum use of rivulet surface, the drag over the surface can be reduced. Rivulet impart movement to the longitudinal vertices. Thus, there is a reduction in the advection near the wall. The detailed concept will help us to design micro-textured surface for a specific field of application. Thank you.
Okay, questions for Vikas? I have one question, Vikas. So what is the roughness of your surface?
So roughness of the rivulet surface I am using.
Yes, how much it is?
Sir, I have not checked it for the like the exact roughness of the surface I am using right now. But
So why I ask, because you are placing a sensor right at the surface. If the surfaces of, the roughness of the two are not matching, for example, your sensor versus the surface, then you may have, the effect of, for example, viscous sublayer. If the sensor is rough as compared to the surface, or surface is rough as compared to the sensor. So are you making sure your sensor surface is on the same order as roughness of your actual surface? Because then you may not see many experimental artifacts.
okay, sir, I understand what you are saying.
Yeah.
But means I am taking the voltage signal from the
Right,
probe.
but that will change if the surface roughness is different, right? Because at the end, you are trying to changing the flow characteristic above the sensor.
Yeah, yes.
All right, something to think about. Let us move to the next and the last talk. And I'm hoping there are no more questions for Vikas. If there are any, we can stop and take. Okay, let us move on to the next talk. It's by Professor Dalal's group, and Neeraj is going to present. Can you play the talk, please?
Hello, I am Neeraj Kumar Prasad, a PhD student in Department of Mechanical Engineering, Indian Institute of Technology, Guwahati. I am going to present my work on studying transport behavior of commercial anti-cancer drug protein-bound paclitaxel, which has a commercial name nanopacli in blood capillary size microchannel. Paclitaxel is a well-known natural source drug derived from the bark of the Pacific yew tree. It is mostly used for treatment of metastatic breast cancer, and it is naturally hydrophobic in nature. And due to its poor solubility in water, it requires a synthetic solvent for its delivery and stabilization. It is constituted with castor oil or chemophore. which can be used in injectable form for the treatment. The synthetic form is, on other hand, increases cytotoxicity and it also causes decreased therapeutic efficacy. To counter this problem, a solvent-free form protein-bound paclitaxel is now widely used for treatment of metastatic breast cancer, lung cancer, and pancreatic cancer, and also in cancer immunotherapy. Commercially, it is most famously known as Abraxane, quite an expensive drug, and it is also known as Nab-Pacli, Nano-Pacli, etc. The newly constituted form of paclitaxel is significant in reducing harmful effects, and it also improves therapeutic efficiency. In my work, I try to see the migration of mass transport of real-life commercially available drug and what happens to its migration and transport when it undergoes a high shear flow in severely constricted microchannel, like blood microcapillaries. Due to its nanoscale properties, they have a tendency of obstructing the capillary in blood vessels, which may be a detrimental effect in cancer treatment. Desai et al. Suggested that albumin-bound paclitaxel of average size 130 nanometer will show less tendency of capillary obstruction. We will try to observe it by performing real-time experiment with nanodrug particles. For this, we fabricated a PDMS-based microchannel. The dimension for the microchannel was chosen as 7 micrometer so as to mimic the mechanical surrounding of blood capillaries. The other dimensions you can also see, it is shown here in this diagram. It has a converging section, it also has a diverging section. The experimental setup consists of an inverted microscope, a high-speed camera for flow capturing, and syringe pump for flow actuation. This syringe holds the sample, and this is a semi-rigid intramedic tube which is connected to the microchannel, which will deliver the solution to the microchannel. This is the vial of drug which we purchased from market. This is Nano-Pacli, known its market name. And you can see for a 100 mg vial, the cost of this medicine is 10,000 rupees. And to make the sample of this drug particle, it already comes in a nano-constituted form. To make a sample, we dissolved 10 mg of the solute in 2 ml of the water. The concentration was mentioned in the guidelines of the manufacturer. This is the microchannel which we fabricated for our experiment. This is the inlet port, this is the outlet port. You can see here I have drawn, and this portion is somewhere in between here. Next, I will talk about the experimental observation which I found by seeing the flow of the drug particles inside the microchannel. The flow of drug particles was captured by high-speed camera at frame rate of 5000 frame per second. The portion of the channel was chosen as this converging section, which has the dimension of 35 micrometer, and it gradually reduces to 7 micrometer at the entry of the capillary. The diverging section also has the dimension, the width gradually increasing to 35 micrometer from the 7 micrometer constricted microchannel. We first saw the flow at a flow rate of 50 microliter per hour. As we can see, the flow at 50 microliter per hour commences without any obstruction. It is a very good sign because the 50 microliter per hour corresponds to the blood flow rate in the veins. It is also comes in the range of the blood flow rate inside our blood vessels. And drug particles seem to flow without any obstruction at this flow rate, which is a very good sign for this drug particle. Then we try to see the flow rate dependency on the transport of these drug particles. So we increase the flow rate to 100 microliter per hour. At 100 microliter per hour, we interestingly saw the detrimental effects like this nanoclustering. You can see that these drug particles have agglomerated at the entry to the microchannel, and they have also blocked the channel, which ultimately caused the capillary obstruction. Along with the capillary obstruction, we also saw that the particles also adhere to the wall. Although this capillary obstruction removed under the flow pressure. Next, we try to plot the x displacement and y displacement of the drug particle inside the microchannel at different instant of time. The displacement and the time measurement starts from the origin as shown in this figure. When the molecules reach at this position, we started capturing the displacement and also the time elapsed. The displacement and time elapsed is measured and captured by using the image processing software, the PCC software of the phantom camera. As the mass transport of solid particles is generally guided by both convection and diffusion process, the mass transfer inside microchannel is mainly diffusion dominated. And because of this, the movement of drug through the vessel wall in the radial direction is brought up by diffusion in intravenous flows. Besides, the transport of drug particles can be better explained by Peclet number, which is the ratio of advective transport to the diffusive transport of solutes. We can check the Peclet number dependency of the drug particle by observing the flow at different flow rates. In our study, we have only chose 2 flow rates. For the conclusion, we can say that the cause of nanoagglomeration can be attributed to the high surface energy of the nanoparticles, which results in nanoclustering and adhering to the channel wall, which we saw at a flow rate of 100 microliter per hour, which can may be attributed to the protein surface of the drug particle. In a positive note, this kind of capillary obstruction is less likely to happen in real intravenous flows. But as we saw, the onset of capillary obstruction at higher flow rate, which also reveals the other aspects of solute transport in microchannel. For the future work, I would like to see the transport behavior of these drug particles at considerably wider range of possible intravenous flow rate. Besides, the non-Newtonian behavior of protein-bound paclitaxel at higher flow rate can also be studied. I would like to thank Department of Mechanical Engineering and Department of Biosciences and Bioengineering of Indian Institute of Technology Guwahati for the financial support. And I will also like to thank the Center of Nanotech Science and Engineering, Indian Institute of Science, which helped me in fabrication of microchannel. Thank you.
All right. Any questions on this presentation?
Hello.
Go ahead.
I want to ask what method they have used to manufacture that microchannel.
Yeah. Hello. That microchannel we use that photolithography technique by using a negative photoresist.
Okay.
All right. Are there any more questions? Okay, then I think you can close the session. The next is the valedictory ceremony. That is at 4, and I think you can check the hall, which hall you have to join. Thank you all for your participation in this session. Thank you.
So at the end, we thank Professor Rajneesh Bhardwaj for chairing this session, and thank you all.
Thank you.
Thank you.
Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Vous allez décrire un instant.
Yes, you are audible, Professor Banerjee.
Yeah, thank you.
Am I audible?
Hard copy.
Am I audible?
Yes, Professor Saha. Yes, Professor Saha.
Yes, Professor
You are
Saha.
audible.
You are audible.
Amras, are you going to start now?
Yes, sir. Yes, sir. Good afternoon. Good afternoon.
Good afternoon.
Good afternoon. सब बंद है ना, इको हो रहा है बहुत. ओके. ये पंकज आगे आप. हाँ. So, okay. Okay, so good evening, everyone. On behalf of our organizing committee, I welcome you all for the valedictory session, and it's a pleasure to have today's chief guest with us, Professor S.K. Kakoti, Deputy Director of IIT Guwahati. So with this, I begin the valedictory session, and I would like to invite Professor Ujjwal K. Saha, Joint the Organizing Secretary, to give the welcome address and brief report on 3 days conference. So over to Professor Saha.
Thank you, Professor P.K. Mishra. Respected
You are not much audible, Professor Saha.
Hello.
Yeah,
Am I audible?
It is okay now.
Am I audible?
Yes, it is okay now.
Am I audible?
Yes,
okay
yes,
now.
Professor Saha.
Okay. Okay, thank you, Professor P.K. Mishra. Respected Chief Guest, Professor S.K. Kakoti, Deputy Director, IIT Guwahati, other dignitaries, academicians, students, and the entire fluid mechanics and fluid power community. Good afternoon to everyone. It is indeed a matter of pleasure for the organizing team to be here during the valedictory session of the conference. Our original plan was to hold the conference in its usual physical mode. However, because of the prevailing pandemic situation, we had to organize it virtually. At the beginning, we were a bit apprehensive on the use of this virtual platform, but today we feel satisfied and relieved that we have been able to conduct it smoothly without any technical glitch. In this conference, a total of 240 technical papers have been presented in the form of recorded videos, and all of them were followed by live interactive sessions. The papers were distributed over 12 different technical tracks and were presented across 36 technical sessions, and the other one by Professor Franz Durst, University of Erlangen, Germany, who delivered the Professor Astato Narayana plenary lecture by eminent academicians from different parts of the country, and this has instigated excellent discussion and interactions between the speakers and the participants. These sessions have been live streamed through YouTube and Facebook, and this has attracted a large number of participants to attend the conference from all over the world. We have received feedback from the session chairs on the technical Best Paper Presentation Award. There are 4 awards decided by Saha
for good summary of the conference. And now I would like to invite Professor Amresh Dalal, convener of the conference, to basically get the feedback by the participants. So over to Professor Dalal.
Thank you, Professor Misra. So I would like to take a few feedbacks from the participants. So you please click raise hand in the Microsoft Teams. So I will just want to know feedbacks because you are the participants and the speakers attended these lectures over last 3 days. So it will be good to hear from you. Please, yes, Professor Natarajan.
Thank you, Professor Dalal. It was indeed a very interesting and different experience attending the conference virtually. I believe most of us will agree on the fact that it is probably a first-time experience for many. Despite that, it was, even though the face-to-face interactions were not there and we couldn't visit the beautiful campus, there were a large number of papers that one could look forward to, greater participation across the country as well. And one of the advantages of streaming the papers over YouTube and Facebook was that since there were parallel sessions, even if you missed out a few lectures, you could always go back and revisit them at your spare time, which was clearly a big advantage. In the sessions that I attended, there were very interesting talks, and a wide range of topics could also be covered by eminent speakers both from India and abroad. So overall, it was a very interesting and fruitful experience. And I would like to applaud the entire team at IIT Guwahati, particularly Professor Dalal, Professor Saha, Dr. Day, Dr. Basu, and all my friends at Mechanical Department at IIT Guwahati for having put up this very wonderful show. Your efforts have really paid off, and I would like to congratulate you on a.
Thank you, Professor Natarajan, for your kind words. Would like to hear from some participants. Okay, please go ahead, Professor. Hello, your name is not there, but Bedin 732. Okay.
So I have experienced all these days what is the culture of IIT. Though I am not conference, it was really fascinating today morning. Arup Das sir and Ashish Sen sir was really, was very fascinating. Moreover, Germany, I don't remember the name of the particular sir who was conducted yesterday morning talk from Germany. That was really, really fascinating. One of the unique kinds. So it was really a pleasant experience for me attending this conference in the virtual mode. It's a really, really mind-blowing experience for me. Thank you, sir. Thank you for this.
Thank you very much. So I would like to hear from Arjun. Actually, he is attending from Japan. So it will be good to hear from Arjun. Arjun Jan.
Thank you, sir. It was, as Natarajan sir has mentioned, it was a nice opportunity, especially since it's in the live streamed in YouTube. We could attend or we could go back to the sessions we missed and could hear the talks from other dignitaries. And one suggestion that I may have is it would have been better if you could share the extended paper with all the participants beforehand, so that we could have checked all the details of the ongoing talks. That is just one minor suggestion from my part. Otherwise, yeah, I would congratulate all the team members and for this wonderful initiative, and all the very best. Thank you so much.
Thank you, Arjun. So I'd like to hear from some session chairs. Professor Bunni Ray, are you there? Professor Bunni Ray?
Yes. Yeah, you can hear me as there's some background noise here.
Yeah, so yeah, it was a wonderful experience. So I session chaired two of the sessions, and I also sessioned the keynote lecture. So the type of talks which were given and the presentations were really nice. And in my sessions also, I asked the students a lot of questions, and I saw that the way they're giving the presentation, the way they're answering, it was really impressive. Yeah, but yes, I missed that the communication would have been better if all were in front, if we're in person. Yeah, that was really missing, but I like the type of paper and the type of presentations which were there. Thank you.
Thank you, Professor Ray. Any other participants? So I would request Professor Atul Sharma to say a few words or his feedback. Professor Sharma.
Thanks, Amresh. I know you were very much passionate about holding the conference in, and we were equally looking forward to come to your campus. But it's very unfortunate that we could not, but I'm now very much satisfied with the way the conference has gone, and highly appreciate, although initially we were really hesitant how to go ahead about this, but you have done a wonderful job and you have more than satisfied all of us. So I highly appreciate the efforts, continuous. I do understand from early morning to late evening, late nights, I should say, all of you have been working. So I really appreciate, and we are really thankful to you and as well as your message for their future endeavors. Thanks a lot for the grand success of the FMFP Conference 2020.
Thank you, Professor Sharma. So I have also noticed many of you have attended many lectures. So Professor Arakeri also attended many lectures I have seen. So I would request to say a few words. Professor Arakeri, if you say a few words. Professor Arakeri.
Thank you very much. Congratulations for a wonderful job. I remember that a couple of months back we were hesitant, but yeah, you've done a fantastic job. And yeah, I enjoyed many of the talks. Of course, I couldn't attend all of them. So one question I had was, are these talks recorded?
Available day-wise. Okay, so if there are no feedback, I would request you to always give your feedback, suggestions through email so that we can know those things, and in the later conferences we will take care of all those suggestions. Thank you very much. So Professor Misra, over to Professor Misra.
So thank you, Professor Dalal. So now we move to the next part of the session, and we would like to invite Professor Jyotirmay Banerjee, who is also Secretary of National Society for Fluid Mechanics and Fluid Power, to address the session. So over to Professor Banerjee.
Thank you. Professor Kakoti, Deputy Director of IIT Guwahati, Professor Amaresh Dalal, the Organizing Secretary of this conference, all the dignitaries, the volunteers who have contributed significantly for the organization of this conference, and my dear participants. First of all, I want to congratulate Professor Amaresh Dalal and his team for the successful organization of the 8th International and 47th National Conference of National Society of Fluid Mechanics and Fluid Power in virtual mode. In the 2018 General Body Meeting of NSFMFP, when IIT Guwahati was given the opportunity to host this conference, we were very excited to meet at this green campus for the first time in northeastern region. But somehow it did not materialize. But I'm happy Professor Amaresh Dalal could create a virtual conference in a grand manner. There were very good speakers, good participation, and very nicely well-timed organized conference. National Society of Fluid Mechanics and Fluid Power was established in 1973 under the able leadership of Professor Subir Kaur. Professor Subir Kaur has had the vision to bring in the industrialists, the academicians, and the research scholars on a single platform. He had, in the beginning, got support from industries like Jyoti Pumps from Gujarat, Kirloskar, and PSG Pumps from Coimbatore. He has organized the first conference from National Society of Fluid Mechanics on Fluid Power in the year 1969 at Jadavpur University. Since then, we have organized 47 conferences. I'm happy that in coming 3 years, we shall be organizing the 50th conference of this society. The society, in addition to this conference, organizes several workshops. The most important of the workshops is a workshop on research methodology in fluid mechanics and fluid power. This has been organized at several places, including NIT Allahabad, NIT Surathkal, Amrita University, PSG Coimbatore, and in this May it was organized at IIT Guwahati. The society has 788 live members and is going strong. I believe in future we will have more members of the society, more activities, and the society will grow and we will be able to organize many more functions of this kind that will benefit the research community in the area of fluid mechanics and fluid power. I once again congratulate IIT Guwahati for organizing this conference on virtual mode at such a grand scale. My thanks to Professor Amaresh Dalal and the entire team. Thank you very much. Thank you all.
So thank you, Professor Banerjee, for your kind words and giving us the futuristic roadmap for conference. And now I would like to move the next segment of the session, that is announcement of the best paper award. And I would like to invite Joint Secretary of Conference, Professor Arnab K. Day, to basically present the award. So over to Professor Day.
Thank you, Pankaj. We are at the fag end of this conference. We are slightly disappointed that we could not arrange the conference the way we would have liked it to. Nevertheless, I hope it's one of its kind in the virtual mode. Taking cue from what Professor Saha already mentioned, I'm going to announce 4 awards for this version of FMFP conference. While the first 2 are instituted by National Society for Fluid Mechanics and Fluid Power, the last 2 is endorsed by Sadhana. The first category is Professor M.G. Deshpande Award for Best Paper from Academia. The title of the paper is Liquid Droplet Morphology on a Fiber of a Fog Harvester Mesh and the Droplet Detachment Conditions Under Gravity. Paper number 191, authored by Aroni Mukhopadhyay, Parthasarathi Dotto, Amitabh Dotto, and Ranjan Ganguly. Though it's a virtual mode, still I would invite a big round of applause for the authors. Moving to the next category. Moving to the next category, Professor Y.V.N. Rao Award for Best Paper from Industry Institution Interaction. The paper number is 72, titled Numerical Study of Nanoparticle Injection in Tumors for Nanoparticle Assisted Hyperthermia, authored by Mitu Sagar, Sanjeev Soni, Sarit Kumar Das, and Himanshu Tyagi. Moving to the third category, Sadhana's Most Innovative Research Award. It goes to paper number 142, paper-based microfluidic pump for point-of-care applications, authored by Boibhav Jaiswal and P.S. Gandhi. And the last one, the award for the best presentation goes to paper number 22, Viscoelastic Droplet Dynamics in viscoelastic matrix. The presenter is Somik Hajra from IIT Madras, co-authored by Susanto K. Mitra and Ashish Kumar Sen. Now, since I have done my job, over to Pankaj again.
So thank you, Arnab. And now we move to the next segment of the session, and we would like to invite our chief guest, Professor S.K. Kakoti, to say a few words and share his thought about the conference. So over to Professor Kakoti.
Thank you, Professor Mishra. I am really honored to be here among you, where many stalwarts are there I have seen, and Professor Banerjee, Professor Dalal, Professor Saha, Professor Dey, an entire team, organizing team, and participants from across the world, as I have learned. Somebody from Japan also participated already, some feedback was also given. All the participants, and I'm really very glad to hear the feedback. Actually, everybody has given very positive remarks about the conference. Yes, it is true that we could not hold it physically. Many of the events are either postponed or cancelled, but some of the courageous and organizers in the institute came up with virtual mode of conference. That is how this FMFP conference is held. From Banerjee, I came to know that this is the 47, which started from 69. The great society work. I must commend the society for organizing this type of event every year, along with some other events. And we are actually a good host. It is said by others. We are very good hosts. IIT Guwahati is a very good host. We like to host people here in our campus. People say our campus is one of the most beautiful campus. And people like the whole ambience here. You say it is guest house, you say it is the department, you say it is the library, computational facilities, other laboratories. So when people come here, they move around and everybody gets their interest here. So that is what is missing. When we normally attend a conference, we always like to look at different, things which are not available around us. Say if I am attending one conference in the US or Germany, we really plan what to see, how to meet some stalwarts, how can we interact with those people, not in the subject matter, but in some other matters also. So that does not happen virtually. That is the only disadvantage. However, this pandemic has actually given us the opportunity to think out of the box. And that is how these virtual activities are gearing up. There are few drawbacks, but I understand with pace of development, these drawbacks will be not there after a few months or even after 1 year. If you have another virtual conference, you will find a lot of improvement, lot of, for example, now when Professor Arnab Dey was announcing these awards, normally in an auditorium, there will be applause, big applause, clapping, which perhaps will come up with some tools which you can produce here also in virtual mode. So these type of things also will come up, I hope, like that. And I must again congratulate the organizing team. With a lot of constraints during this pandemic, they have taken all the pain, not only to organize this, but to culminate this whole program very nicely. I am amazed to understand that 240 technical papers were presented during this conference. It's a huge number, actually. Of course, there are parallel sessions, but I also learned that these are in the YouTube, and also in the website also this will be uploaded, these videos. So anybody can browse and see. If you have missed some of the lectures, you can always see. And also the plenary lectures and keynote lectures were addressed by very prominent researchers, including our former director, Professor Biswas. He is a real very highly acclaimed researcher. So with that, actually, the conference gets a different, sort of a level. So that is also maintained. That is very good news. So overall, on behalf of the institute, I thank all the participants, all the sponsors, and particularly the FMFP Society for giving this opportunity to this institute, IIT Guwahati, to organize this conference, which is the 47th national conference, and I think, if I'm not wrong, it is 7th international conference. Am I right? Okay. So we hope in future we'll be having physical conferences. Many of you will be having the opportunity to come over here, and we are waiting. We're very eagerly waiting for that. And in fact, recently I was involved in an event which we had made actually partially physical and partially virtual. So it was in a hub and spoke mode. So that also is a new thought actually. Actually, how it was done, the main gathering was here, very limited gathering. Here it was around 60 to 80 persons gathered, transacted different sessions, and it was live for 8 different hubs at different places over the country. And beyond that, many people connected through their own laptop or mobile smartphones. So that way the participation finally, when we found, it was amazing. It was 10,000 plus participation was there in the event. So these are the beautiful things actually about virtual meetings. In virtual meetings, if you live stream in social media like YouTube, Facebook, you get many more participants, not only the presenters, there will be more audience, more viewers. So that these are the beautiful things about the virtual events. So we'll be improvising this type of conferences in future. Having any unwarranted disadvantages, we'll try to mitigate that in future. And I welcome all of you. Whenever the situation improves, please try to make a trip to IIT Guwahati. We'll be hosting you very nicely here. With these words, thank you very much. I again thank the organizers, particularly Professor Dalal, for inviting me to interact with the participants in this valedictory session. Thank you very much.
So thank you, Professor Kakoti, for sharing the thoughts of the IITG community to the FMFP Society. So with this, we move to the final segment of the session, and I would like to invite Professor Tapan Mankodi to deliver the vote of thank you speech. So over to Professor Mankodi.
A very good afternoon to everyone. Thank you, Professor S.K. Kakoti, Deputy Director, IIT Guwahati, and the Chief Guest of this valedictory function, for kindly accepting our invitation to address this occasion despite of your busy schedule, and for sharing words of wisdom with us. On behalf of the FMFP Organizing Committee, I would like to begin the vote of thanks by expressing our gratitude to the National Society of Fluid Mechanics and Fluid Power, and to Professor Jayawant Arakari, President of NSFMFP. We also thank Professor Jyotirmay Banerjee, Secretary, for his kind words. Indeed, conducting FMFP in virtual mode has come with its own set of challenges, and a successful organization wouldn't have been possible without the constant encouragement from the NSFMFP. We must mention our deep sense of appreciation to our plenary speakers, Professor Gautam Beswas and Professor Franz Dust, and to all our keynote speakers. We are grateful that you all could attend the conference from different parts of the world, even if that meant joining us at odd hours due to different time zones. Over the last 3 days, we have witnessed thought-provoking talks, and all this have been possible because of the support received from the reviewers, session chairs, and most importantly, the participants. We would like to acknowledge the support received from our institute administration and from our department. In this regard, we wish to express our sincere gratitude to our director, Professor T.G. Sitaram, and HOD, Professor S. Senthilvelan. We have been fortunate enough to be backed by a team of very motivated volunteers who have spent days learning the modalities of the virtual conferencing and also testing and conducting dry runs several times. I cannot thank enough for their involvement and contribution for the smooth conduct of the conference. If I miss out on thanking anyone for their contribution, I sincerely apologize for the same. Finally, I conclude the conference by again thanking you all. Thank you.
Okay, so thank you, Tapan. And now, as you know, that everything has to end, but we are ending here as a very positive note, and hopeful to see you all in the next FMFP conference. And before concluding the session, I would like to invite all the volunteers, student volunteers, please get together at one place and yeah, so these are our the working horse of the conference. They basically devoted their day and night time since last 1 month or 2 months. So in order to bring this first of this kind of conference into the reality, and we are really proud of them. And so let's have a big round of applause for all our volunteers. Okay, so with this, I thank you all again for attending this voluntary session, and I would like to say goodbye and see you all in the next conference of the society. Bye bye.
Bye. Thank you.
Thank you. Thank you.
Thank you.
Thank you, Professor Amresh.
Thank you very much.